There we go. Why does it say that we are waiting? There we go. All right. There is a delay here. I'm trying to figure out how long it is. Oh boy. Okay. I'm just gonna, oh, that's a nice handprint. I'm just going to get on Remind very quickly and send out the link to this. Oh, good. I don't remember my login information. That might be it. Oh, that is it. Sweet. Okay. Okay. I'm just going to send out a quick blast message and we will get moving. And this is to all classes, right? Okay. Announcements are going out. We're going to get started in like 1 minute. For everyone's reference, we're working on January 2012. Okay. That should be it. Hi. Okay. Super quick. If you're not on Remind already, we are going to have new people join the 216 Remind. And that is to text at G3494C281010. Okay. I don't know where my frame is here. Oh, and this is really delayed. Okay. We are working in January 2012. This is really delayed. This is going to be fun. Okay. That is enough of that. Moving on. We are... Okay. Oh, God. Okay. We are working on January 2012. Let's get started. I almost want to like... I kind of want to set up like a mirror because the way this is set up, it's so funny. I have this laptop is folded to look at the table. And I'm using a second laptop to watch it, but it's really like a 10-second delay, if not longer. Hola. Okay, fastest way to get in touch is going to be through Remind, honestly, because the delay is like kind of crazy. Okay. Everything just got blurry. I'm sorry, guys. I'm not very good at these things. You know this by now. Okay. I also don't want to put my ugly face on the internet. So, I may have to put my ugly face on the internet to get this to work. Okay. Let's just get started. Okay. Question 1. What is the number of electrons in a completely filled second shell of an atom? Okay. That is a question for the reference tables. Tell me all my reference tables are in the car. I did. I left all my reference tables in my car. Because I'm a smart lady. Okay. Which means I'm going to print one right now. Okay, go grab a snack. Give me 5 minutes. I'm going to try to resituate this. This is kind of crazy here. Okay. First off, let's print a reference table. Okay. Okay. Oh. Welcome to my basement. Why isn't this printing? Okay. Okay, we're gonna have to do this the fun way. I have no idea what I'm doing right now. Okay. I'm watching myself on the computer over here. My desk is a disaster at home too. Okay. I think we should just do it this way, because then I can actually see what's going on as it's happening, because the delay on this is actually pretty drastic. It's really like 20 seconds. And when I did this in January, I had an extra camera that I could like point at stuff, but I borrowed it and I don't have that. So the only camera I have is built into the computer. So I can't see what's happening as it's happening. Oh, it's so hot. Okay. I'm sorry, this is taking forever. I'm the worst. We're only up to table H in the printer. Okay. Question 1 is going to come on the periodic table. The orbitals, the shells, are on the bottom. They're listed on the bottom of the periodic table. What is happening to this thing? So, let's see. On the periodic table, maybe this will work, but it's still going to be backwards. But I can at least kind of see it. Okay. On the periodic table, you have a box. It will say neon, and then it says 2-8, and that's neon's electron configuration. This is the first shell. This one is the last shell. The last shell is called the valence shell. I'm sorry about the printer. That's the valence shell. this is a completely second filled shell. So you would have to go to period 3 of the periodic table to tell you how many are in. Oh no, this is asking for a completely second filled shell. Completely filled second shell right here. So that's that. Neon is the answer. Neon has 8 electrons in its valence shell. So the answer to number 1 is 4. Okay. Question 2. What is the number of electrons in an atom that has 3 protons and 4 neutrons? The key word here, I'm sorry, are you seeing the same glare I'm seeing? Okay. The key word in this is atom. Atom means that it is electrically neutral. So electrically neutral would mean that there are the same number of protons as there are electrons. So that's just kind of like vocabulary. So if it has 3 protons, that's 3 positives. Neutrons are neutral. So in order for this to be an atom, you have to have the same number of protons and electrons, which would mean you need 3 electrons. That's the definition of an atom. When you have electrons being added or taken away, that's called an ion now. I-O-N, ion. I've got my eye on you. Yeah, that's when your atoms have charges. So number 2 is 3. Awesome. Okay. Question 3. As a result of the gold foil experiment, it was concluded that an atom has what? I hope you have this test in front of you. Pull this test up in front of you. Here's a question. Can we go back to number 1? Is the last element of the periodic table considered complete? Yes, anything in group 18 is a full shell. They are the noble gases. They are noble because, oh good, I'm out of ink. Table S. Okay. Everything in group 18, these guys have a full shell. That's what makes them noble gases. They're also called inert gases. They don't want to react with anybody else. What else do we have here? Sweet. Okay, back to question 3, the gold foil experiment. Rutherford and the gold foil experiment, that's when we took the hula hoop with the styrofoam ball in the middle and we threw the ping pong balls through it. The styrofoam ball was the nucleus. And then we have, I'm just going to draw it real quick. We have a sheet of gold foil. It's kind of like aluminum foil, but it's made out of gold instead. I'll flip this around in a sec. Then Rutherford has this lead box that has just a tiny little hole in it. And inside this box, he put, I don't remember what it was, but it was something that was going to have an alpha decay. So looking at table N, let's just assume for fun that this was plutonium-239 because that is going to have alpha decay. So when this decays, the alpha particles are going to come out of, it probably wasn't plutonium because its half-life is actually very, very long, but it's something that has alpha decay. So we have alpha particles coming out of here. If you forgot the format for an alpha particle, that is on table O. That is this guy right there. alpha particle. So the alpha particles are coming out of the box. They're headed towards the gold foil, and there is like this catcher around the gold foil, and it wraps all the way around like this. And what happens is this thing, as it gets blasted with the alpha particles, it makes little like pinholes, like almost like it was poked with a pin. So most of these pinholes were back here, which tells Rutherford that most of these alpha particles are flying straight through the gold foil as they hit the catcher. This is like 99%. Then it's something like 0.5% come through and wind up somewhere over here or over here. These are the ones that came in and then went wow and made a detour. And then there was like 0.5% that hit the gold foil and then bounced back, and they came out somewhere over here. So all of this together tells Rutherford that he knows that alpha particles are positive. That means because 99% go straight through, the atom must be mostly empty space. These things tell him that whatever is inside the atom, this nucleus, must be positive, because the two positives are going to repel each other. These positives come in from over here, they see the nucleus, and they go, hey, you're positive just like me, and then they go swinging out to the side. The very small number that bounce back are the very small number of alpha particles that came in, hit the nucleus, and then bounced back. So Rutherford decides that the atom is mostly empty space because most of it went through. He decides that the nucleus is positive, and it is very small and very dense. Where is it? Can you see all that? I'm sorry. Okay. The atom is mostly empty space. The nucleus is positive, and the nucleus is very small and very dense. So going back to the question, that would be choice 2, contains a small dense nucleus. Positrons and orbitals is part of the wave mechanical model. That's from choice 3. Choice 4, hard indivisible spheres. That's that guy, John Dalton. If you remember when we did the candy for the atoms and stuff, the hard indivisible spheres for most people was the gumballs. And then choice 1 contains protons, neutrons, and electrons. That is certainly true, but that's not Ernest Rutherford. That is a combination of lots of different guys. Rutherford doesn't know that there's protons or neutrons. He just knows that the nucleus is positive. He's not sure that it's protons. The neutron is J.J. Thomson. The electrons and the protons come from that plum pudding model that you may or may not remember. That's the one where the atom's kind of like a chocolate chip cookie. In the good old days, they had pudding that had raisins in it, and they called it plum pudding, which is so disgusting. The pudding was positive, and then there were negative electrons all throughout, and it kind of looked like, in their day, plum pudding, but Ms. Nicholas calls it chocolate chip cookies because they definitely taste better. So that's the plum pudding model, which I like to call the chocolate chip cookie model. I think we need to start a movement to officially rename this because this is gross. Plum pudding. Okay. Number 4, which statement describes the distribution of charge in an atom? So this is asking how we see it now. How we see atoms today in 2017. So just a reminder, the first 30 questions, 1 through 30, really should not require you to do very much math. It's mostly reading the reference tables and vocabulary. So if you're going to cram for this test, cram vocabulary. I promise it's the thing that's most worth it. Okay. So the charge distribution in an atom, choice 1, we have a neutral nucleus. That's not true. We know that's not true because there's protons in the nucleus. Can't write on this. Everything went through. Okay. The model of the atom as we see it now is that we have in the nucleus, we have positive protons and neutral neutrons, and they are surrounded by rings of electrons. Now, this is where chemistry kind of gets funny. Until like 1907-ish, this is how we saw the atom. We saw it kind of like a copy of the solar system, where the electrons would be in these rings. We called these rings orbitals. We called them energy levels. We call them, we don't call them clouds yet. Orbitals, energy levels, what's the other word? Quanta. That's a plural of quantum. So this is the Bohr model. This is where electrons can jump around and jump between the levels. In the modern model of the atom, these rings became less distinct and more or less became the fluffy clouds of probability. When we did the candy models of the atom, this would have been your marshmallow, the fluffy clouds of probability. So you are very likely to find an electron somewhere like in this purple space, but in this orange space in between, you are really probably not going to find an electron. It just became like this big fuzzy ball of electrons flying around someplace, and you were more likely to find them here than you would in between the levels. As kind of weird as that sounds. So we know that the overall charge of the nucleus is going to be positive because it's full of protons, which are positive. Then these quanta, orbitals, energy levels, when we start making them fluffy, we start calling them electron clouds. This area is all going to be negative because that's where the negative electrons swim around. That simple. So going back to the question, 1 and 2 are out because we do not have a neutral nucleus. We have a positive nucleus. And we have negatively charged electrons, so that makes this choice 4. If you forgot which particles had which charge, which is totally okay, there's a lot to learn in chemistry, this information is on table O. The beta particle is the fancy name for an electron. Alpha particles are Ernest Rutherford. I'm sorry about that light. Gamma radiation is just energy. Neutrons are neutral, protons are positive, and positrons are kind of like a positive electron. They have no mass, but a positive charge. This is only important in nuclear chemistry, which we just got finished learning. Okay, so that makes number 4. Question 5. Which atom in the ground state has an outermost electron with the most energy? We're looking between cesium. What are we looking at? We're looking at cesium, potassium, sodium, and who? Lithium and sodium. This is a question for the periodic table. Anytime you're asked to compare elements, check the periodic table of elements. That seems kind of burned into my memory, burned into my brain. Look at the periodic table. I'm crazy. So we are looking between cesium, potassium, sodium, and lithium. Because these guys are all in the same group, just a test-taking strategy, it's usually not the ones in the middle. It's going to be one on the top or on the bottom. That narrows you down to 50-50. I'm going to change this light because this is kind of annoying. Is anybody else being blinded? Holy moly. Darkness. Maybe I'll just shine this light right in my face and blind me, but not anybody else. Is that better? If it weren't so rainy and yucky out, it would be wowzers. That doesn't help. That makes things creepy looking. Okay, is that okay? Which question are we on? We are on question 5 right now. Okay. Is that better? Is that worse? I'm not sure. I'm sorry. Back to question 5. We are looking at lithium, sodium, potassium, and cesium. Between those is going to be one on the top or one on the bottom. That's really the only thing that kind of makes sense. So now the question is, what's different about these guys? They have the same number of valence electrons. What comes next? They have different numbers of shells of electrons. So if you were to draw a lithium, which I'm going to do, it has 2 shells of electrons. It has a positive nucleus, which is +3. It has 2 shells. Sorry, I'll turn this around so you can see instead of me being selfish and hogging it all to myself. This right here is a lithium, +3 and 2 shells of electrons. Then I'm going to jump down to cesium, which is a, oh, I can't do 5, it's upside down. I'm not that talented. We have 55 positives in cesium, and we have 6 shells. 1, 2, 3, 4, 5, 6. This shell has 1, just like lithium. Then in here we have 8. We have 18 here. We have 32 here. Excuse my disgusting kindergarten handwriting there. That's 32. Here we have, oh no, that's francium I'm looking at. We don't have 32 there. We have another 18 right here and 8, and then there's 2. So this is asking you who has the most energy in on their outermost electron. So this is how it goes. This is a potential energy question. We are looking between this electron and this one. The further an electron is from the nucleus, the more energy it has. I think of this like jumping out of a building. As weird as that sounds. When I took physics, this is how my physics teacher taught me potential energy, and that's how I think about it. If you were to jump out of the 2nd floor of a building, let's say a floor is 10 feet, this is a 20-foot jump. This, you are probably going to maybe break an ankle. This 6 shells out would be a 60-foot jump, which is like broken legs, broken ribs, cracked skull. Like, this one's not pretty. So the reason this one is so not pretty is because there is a much greater distance for the fall. In terms of chemistry, this electron is so far from this positive nucleus, and all of these electrons in the middle are blocking, or the chemistry word is shielding this electron from the attraction from these protons. This guy, on the other hand, is very close and is only blocked by 2 electrons. So this guy does not have a lot of freedom. He's pretty much stuck to this lithium. This guy is going to like pop off super, super, super easily. So this guy has more energy. So for question 5, the answer is cesium because it is the furthest away. Its electron is the furthest away from the nucleus. Question 6, which particle has the least mass? Now, if gamma radiation were a question here, although it does have the least mass, it's not a particle, so we wouldn't be able to pick that one. This one, we're going to look at Table O. Table O tells us all about the subatomic particles. Table O is on page 7. According to Table O, we're looking between alpha, beta, neutron, and proton. Now, in your brain, you should know that a proton and a neutron have the same mass. They just have different charges. So one can't have less mass than the other if they're equal. So those guys get eliminated. Alpha particles have a mass of 4. The number on top is the mass number. The number on the bottom is its charge. And then the beta particle is the fancy name for an electron. So if you notice, it is a 0 and a -1. So its mass is 0 and its charge is -1. It has no mass, which is only mostly true. Electrons have a mass that is almost 1/2000th that of a proton. That was a question on a test recently in class or a Regents exam. I don't even remember. If a proton has a mass of 1, then an electron would have a mass of 1, and then it's like 1836 or something. That's the comparison. So an electron is almost 2,000 times smaller, than a proton. So question 6 is 2. That is a beta particle. Okay. Sorry, I just paused to check for mind. So far, there's no questions. The elements, question 7, the elements in group 2 are classified as, okay, periodic table. Periodic table, the groups are the ones that go down, the columns, and the periods are the ones that go across the rows. Group 2 begins with beryllium, magnesium, calcium, strontium, barium, and radium. That's group 2. These guys are called metals. There is this staircase line here. I'm just going to draw on the periodic table while I explain this to you. The staircase line is the dividing line between protons. What am I saying? Between metals and nonmetals. Anything that touches 2 sides of the staircase, with the exception of aluminum, is a metalloid. So I'm going to circle those in this light green color. That is boron, number 5, silicon, number 14, germanium is a plant, germanium, number 32, arsenic, 33, antimony, 51, which is Sb, tellurium, number 52, and polonium, number 84. These guys that are circled in green, those are your metalloids. They are somewhere between a metal and a nonmetal. Everything from here across are metals, and everything from here this way are nonmetals. These guys like to gain electrons. These guys like to lose them. These guys in the middle are weird, and mostly in Regents chemistry, we don't touch them. For metals, you're going to want to remember MELPS, because MELPS helps. MELPS helps you remember that metals, electrons lose positive and smaller. When metals lose their electrons, they become positive ions, and they also usually lose a shell, so they shrink. So question 7, elements in group 2 are choice 1, metals. The noble gases, as said before, are the guys in group 18. These all have a full valence shell, which means that their last shell is totally filled. In neon through radon, this guy UUO, it's been renamed. They haven't updated the Regents tables yet. This is man-made, so we don't usually worry about it. But from neon to radon, number 88, these guys have 8 valence electrons. Helium only has 1 shell, and in the first shell, we can only fit 2 electrons. So it follows what's called the duet rule. If you take enough of these tests or you review enough of them, you come to realize that most of these questions are really repetitive. Number 8, which list includes elements with the most similar chemical properties? You have seen this question, I'm sure. Maybe not with these answer choices, but you've seen this question a number of times. Immediately in your brain should think valence electrons, and it's whoever's going to have the same number of valence electrons. They are going to try to trick you, and here's how. We are asked for choice 1, bromine, which is right here, number 35. I'm looking at this backwards. It's a mirror image for me, which is why I'm constantly like peeking around. Gallium, which is 31 right here. And then mercury, which is number 80 over here. These guys are nowhere near each other on the table. And they kind of like make this, they don't even make a shape. It's not even an L. It's not diagonal. They have nothing in common. Literally nothing is the same about them. In fact, one is a metal. Actually, 2 are metals. Okay, no. Here's something that's similar about them, actually. Bromine is a liquid. Mercury is a liquid. They're the only 2 liquids on the table. And gallium, if you hold it in your hand, it'll melt. But if it's sitting out on the table, it's a solid. It has like the second lowest melting point out of all the metals. So some tables will sometimes say that it's a liquid, even though it's definitely a solid. So that's that. Choice 2 is chromium, Cr. Then lead, which is 82. Where is it? Over here. And then a noble gas, xenon, over here. 2 metals and a gas. They don't have very much in common. Choice 3 is the answer. That is oxygen, sulfur, and selenium. These guys are in the same group, and they have the same number of valence electrons, which makes them very similar. And then choice 4 is nitrogen, oxygen, and fluorine. Some people will try to pick this because they're still in a row. They're in the same group. They're all diatomics, but they don't react similarly at all. Nitrogen is inert. It doesn't want to react with anybody. Oxygen is an oxidizer. It allows fires to continue happening. And fluorine is a poisonous gas. These guys, way more similar because they all have 6 valence electrons. So number 8 is 3. If anybody wants me to speed up or slow down, just let me know. Okay. Number 9, the notation for the nuclide cesium-137 gives information about what? Now, the 137, 55 cesium. Okay. Flipping down. This number up here is the mass number. I should have written all of this beforehand. Wouldn't that have been smart? This is the mass number. This tells you the number of protons and the number of neutrons. This here is called your atomic number. And that tells you only the number of protons. So if you needed to find out the number of neutrons, you could subtract and figure out the number of neutrons. So I'm going to do that. 137 minus 55. And that gives us 82. 82 neutrons in cesium. That's okay. They don't have to be equal. The only thing it has to be equal is the number of protons and electrons if it is an atom. So this guy has 82 neutrons. So going back to the question, this notation will give you the mass number and it gives you the atomic number, which is choice 3. Okay, just a reminder, YouTube is recording this, so if you find that you can only sit for an hour or you have to go or there's something going on or you want to check this out again tomorrow or Monday before the test, you're free to do that. Okay, number 10. Which pair represents two forms of an element in the same phase at STP, but with different structure and different properties? Okay. This is asking you if you know how to read chemistry, which is not always the easiest thing. There's a few keywords here. One is that these guys are going to be in the same phase. So if we are looking at these guys in the same phase, I'm just going to fold this paper in half. If we're looking at these guys in the same phase, we want the little subscripts in the parentheses to be the same. S is for solid, L is for liquid, G is for gas, and AQ means aqueous, dissolved in water. So knowing that we want them in the same phase, we can rule out choices 1 and 4 because they don't have the same little subscripts. Now, we also want them to be the same element, which means they have to have the same symbol. In choice 3, we are looking at hydrogen and mercury. They both start with H, but they're not the same element. And in choice 2, we are still looking at oxygen. It's just one of them is O2 and the other one's O3. Still oxygen. In fact, O2 is oxygen like that we breathe, and O3 is ozone, the stuff that's up in the atmosphere. But it's still oxygen. So the answer for this is choice 2 because it's in the same phase and it's the same element, and 3 is wrong because it's 2 different elements. Okay. Number 11, the elements on the periodic table are arranged in order of increasing what? Somebody's vacuuming. Okay, so if you didn't know the answer to this off the top of your head, you could look at the periodic table and go from there. Atomic mass is mostly true, but not always true. If you look at cobalt and nickel, number 27 and 28, right here. Cobalt is 58.9 and nickel is 58.6. Your mass is going down right there. If you look at, what's one that's a little bit more obvious? If we look at atomic mass is mostly true. I promise it's not always true. It's somewhere in the transition metals. I'm still looking for it. Oh, come on. This is embarrassing, isn't it? Okay, well, that's one right there is iron and, cobalt and nickel. Okay. Okay. So atomic mass is not the answer. It's definitely here somewhere. The atomic number is the answer because the big numbers on the bottom, if you forgot, this big 6 here is your atomic number. So those go in numerical order. The atomic number is also the number of protons. The molar mass has to do with its atomic mass. It's the same thing. And then oxidation numbers are all over the place. If you look in these transition metals, the reason they're transition metals and they're the weirdos in the middle of the table is because they have multiple oxidation states. That really doesn't make much sense. The entire table goes in order of atomic mass. So 11 is 1. Then we have 12. What is the IUPAC name for a compound ZNO? Okay. That vacuum is very loud. I apologize. ZNO. This is where we have to do a reverse crisscross. The charge on a zinc comes from the periodic table. It's +2. That's the oxidation state. It is right here in the corner. We have a +2. Oxygen is over here. He is always, always -2. When we crisscrossed these, you get ZN2O2. And because it is ionic, we can reduce it. These guys come in a crystal lattice, which if you remember is kind of like a checkerboard. And we're looking for the smallest unit of Zn that we can get. So it really looks like Zn with an O with another Zn with an O, like this. It arranges itself in a checkerboard, and chemists say, we can skip writing those 2's because this is essentially the same as this. So they reduced it, which gives us just ZNO. Now, the name for this has to do with your rules for ionic naming. IUPAC is just the scary group of people who sit around and do nothing but name chemicals. They're the most boring people on this planet, probably. Anything that ends in an 8, like in choice 2, oxalate, that should send you to table E. Oxalate is the ion right here. C2O4, which is not in zinc ZNO. That carbon is not there, so it's not zinc oxalate. Zinc peroxide would mean that it has this polyatomic ion, which is O2 with a -2 charge, which we don't have. We have O with a -2 charge. And then hydroxide should ring a bell as being the base ion is right here. Hydroxide, OH-, also not it. So that leaves us with zinc oxide. Whenever we have something that is bonding ionically, the metal keeps its name. So zinc stays zinc. And if you forgot what Zn is, table S will remind you. If I had all of table S, that would have helped, but I already know it. It's fine. The symbols are right here. You would look for ZN, which is number 30. So for number 30, we have the symbol ZN, and its name is zinc. So that's how you know it's zinc. And O is oxygen, if you forgot that. It's also up here on table S. The metal keeps its name. The non-metal gets an "ide" ending. So oxygen becomes oxide, and "ide" is there to tell you that it has bonded. It's like getting married and changing its last name. Oxide. That's zinc oxide. Now, if zinc were a metal that had more than one charge, then we would have to give it a Roman numeral to tell you which charge it was. So just for fun, let's say I had MnO and I needed to name this. I have to go to the periodic table and figure out what charges I have. Well, oxygen's really easy because it's always -2, but manganese, Mn, number 25, has lots of different charges listed there. So how do I know which one it is? I have to uncrisscross. So if oxygen has a -2, I had to have brought the 2 down here when I crisscrossed them, right? So that would mean I have Mn2. And then I would also need to have put a +2 on the manganese to bring the 2 down to the oxygen to get MnO2. And because it's ionic, I can reduce this to MnO, which is exactly what I had. So the next thing would be to figure out how to name this. Manganese has lots of different charges. It has 4 listed there, but it actually has a lot more in reality. Manganese is like the funniest metal on the table. So this would be manganese. If you don't know how to spell it, check out table S, because that's a really easy one to switch up with magnesium, which would give you the wrong answer. This is manganese 2 oxide. And this Roman numeral 2 corresponds to its charge, not how many there are, not how many letters there are, not where the 2 falls on the list on the periodic table, because there's 4 listed there. This 2 literally moves down here. It's the charge. And you would just say this, manganese 2 oxide. So 12 is 1. That was a tangent. How do you know when you can reduce? You can reduce only if it is ionic, which means you have a metal bonded to a nonmetal. Metals are everything on this side of the periodic table. Staircase to the left. The metals are losers. They're on the left. So if you have something from over here and something from over here, and they transfer their electrons, that's how you know when you can reduce. Number 13, which atom attains a stable valence electron configuration by bonding with another atom? Now, you are given choices: neon, radon, helium, and hydrogen. My strategy would be to go to the periodic table. My answer choices are elements. I'm going to check out the periodic table of elements. You are looking between neon, radon is Rn down here. If you don't know, look at table S. It's Rn, not Ra, which is over here. This is radium. Radon is over here. This is one of those things, like, use your reference tables. Bromine, barium, beryllium, and boron all start with B. but only one of them has a symbol that's just B. If you are like only 99% certain, check table S. You have all the time in the world for this test. Not really, you have 3 hours, but I really don't think you need 3 hours. If you know your reference tables and you know your vocabulary, you can very easily finish this test in just 2 hours. And then you have an extra hour to check your work and to take your time and check table S all day long. You are looking between helium, neon, radon, which are all things in the same group, and then you have hydrogen up here. Now, test taking strategy, these guys are all in the same group, so it's probably not one of them. It's probably this guy. And that's true. And here's the chemistry reason. Helium, neon, and radon all have a full valence shell. This hydrogen here only has one valence electron, and it wants to gain one more to fill its valence shell. There you go. 13 is 1. No, 13 is 4. 13 is 4. It's hydrogen because hydrogen doesn't have a full valence shell. Chemistry is all about the electrons. You're going to be looking at the periodic table like crazy, and you're going to be looking at table S like crazy. And those are like the two main tables, table S and the periodic table. You're going to wind up using everything, but those are like the two biggest ones, because they tell you about the electrons and then they tell you names and symbols and things that you may have forgotten about the periodic table. Okay. Number 14, ionic bonds can be formed when one or more electrons do what? Now, this is a bonding question. There are technically 3 types of bonds. You have, I'll flip this around for you in a minute, but we have ionic bonds, we have covalent bonds, and then we have metallic bonds. Metallic bonds are when we have a chunk of a metal. I'd like to say chunk because most metals are solid, but I'm finding more and more that the questions are revolving around mercury. So this is going to be an elemental metal, which really just means a metal all by itself. Covalent is a non-metal and a non-metal together, and ionic is metal and non-metal. These guys, you're going to have a chunk of, really, you're going to have a bunch of nuclei. They go like this, because most of the time they're solid. And what happens is that they kind of share their electrons, and they like kind of swim through the metal. They call it the sea of mobile electrons. And they just kind of like wrap themselves around the nuclei and swim around. This moving electrons is what makes metals malleable, which means A-L-L-E-A-B-L-E, which means they can be hammered into thin sheets. We have ductile, which means you can string them, like you pull them and they string out into wires. It makes them shiny, and it makes them conductive. And that's conductive of both heat and electricity. Then we have covalent bonds, where we have non-metals bonding to non-metals. Non-metals are looking to gain electrons. And because they both want to gain, they have to compromise. And when they compromise, they wind up sharing. This is where you're going to have single, double, and triple bonds. Covalent things typically have lower melting points. A lot of them are found in the gas phase. That's things like oxygen, methane, even butane is a gas. The butane that's in a lighter, they have to like take the gas and squish it so much that it becomes a liquid. That's why it looks like it's a liquid inside a lighter, but it's actually floating around in the atmosphere. It's actually a gas. Ionic things, on the other hand, you have a metal that's looking to lose and you have a non-metal that's looking to gain, and they don't have to compromise. This loser gives his electron away. So here we have a full transfer. You are going to have full charges, which means one becomes positive and one becomes negative. You have a formation of ions. And in doing this, you make ionic bonds. Ions, ionic. So question 14 is asking, an ionic bond can be formed when one or more electrons Sorry, I'm pausing to read a question. That is true, only in covalent bonds. I don't know what that means. My guess is that's in reference to melting and boiling points. Melting and boiling points are typically lower in covalent things because they share. In ionic things like salt, NaCl, these guys are going to have astronomically high boiling and melting points. If you think of ionic things like the salt that you put on your French fries, you, as a human being, have never seen salt in the liquid phase. You've never seen it melted. And that's because its melting point is crazy, crazy high. If you put salt on French fries and then cook them in the oven, they come out and the salt is still in its solid phase. That's because its melting point is ridiculously high. Ionic things usually dissolve very easily, but that's not the same thing as melting. That is dissolving. That's entirely different. That kind of stuff is on table F. This table that nobody likes. That's where your dissolving is going to come in. But its melting point, crazy, crazy, crazy high. So for question 14, we are transferring electrons. So 1 and 2 are out. And for choices 3 and 4, we are looking between transferred from the nucleus or transfer from the valence shells. Now, electrons are not in your nucleus. So not only is this a bonding question, it's also an atomic theory question. But also, your electrons that are bonding and exchanged in bonding and all that jazz are the electrons all the way on the outside. Because if you, even here, these electrons are moving at the speed of light. They're moving crazy fast. So this guy is blocking all of these other inside electrons from having any fun. They're totally blocked. It's only the valence shell that gets to play. That's why all year we've been talking about the valence shell. The rest of the electrons usually don't matter. Like 98% of the time, these inner electrons, which are sometimes called core electrons, don't matter. It's all about the valence shell. So 14 is 4. Your electrons are transferred from the valence shell of one to the valence shell of the other. Question 15, which sample of CO2 has a definite shape and a definite volume? We have CO2 aqueous, gas, liquid, and solid. This is a vocab question. Definite shape and definite volume. This is like a 4th grade question, maybe. AQ means dissolved in water. That doesn't have a definite shape. It does have a definite volume, though. Gases, no shape, no volume. I mean, they have volume, but they take whatever volume is in the container. So if I took, I don't know, a breath of air and I put it in a space this big, it's this big. If I put it in a space this big, now it's this big. Liquids do not have definite shape or volume. The answer is solids. Solids are the ones that have definite shape, definite volume. That's that. 15 is 4. It's just vocab. But the part of this that is chemistry is, again, reading these little like subscripts in the parentheses, knowing how to read that. 14, what occurs in order to break a bond in the chlorine molecule, Cl2? This is barf. In BARF, which is an acronym, when bonds are broken, energy is absorbed. When energy is released, that means a bond has been formed. Break, absorb, release, form. Now, we are looking at Cl2. In order to break the bond in Cl2, break, absorb. Energy is being absorbed. Now, that's choice 1. Choice 2 is just wrong. And choices 3 and 4 are impossible. Now, you and I are mere humans. We do not have power to create or destroy energy. According to the law of conservation, which is also the first law of thermodynamics, creating and destroying energy is not allowed by nature. Like, nobody has this power. It's not that it's like we haven't figured it out yet. According to this law of nature, it's never going to happen. Energy can be exchanged from one form to another. We can take kinetic, turn it into potential. We can take chemical, turn it into electrical. We can take any form of energy and transfer it into any other form. But we can't create it. We can't destroy it. Okay, 16 is 1. Okay. Now we have number 17. We have a sealed, rigid 1-liter container that contains helium gas at STP. An identical cylinder contains neon gas at STP. The 2 cylinders contain the same number of what? Now, this is Avogadro's law. If I have a sealed rigid container, just means it's not a balloon. It's stuck in its particular shape. So like here, this is a bottle. This is a rigid container because I can't expand it. But if I had a balloon, which I don't have on my desk, you know, balloons are stretchy. That's expandable. A rigid container means it's just not expanding. These are both 1 liter. And inside this one, we have helium. And inside this one, we have neon. I'm sorry, I'm writing upside down. According to Avogadro's law, if you have gases at the same volume, and it's also saying that these guys are at STP, which is standard temperature and pressure. If you forgot what that is, it's on table A, which is right here, standard temperature and pressure, which tells you that they are at 1 atmosphere and 273 Kelvin. These guys are under the exact same conditions. Avogadro says they have the same number of particles. Now, this is where the idea of the mole came from. Avogadro didn't come out and say, oh my goodness, this is a mole. They have the same number of atoms and molecules. That number is 6.02 times 10 to the 23rd. He didn't come up with that. He came up with this idea that if you had two gases at the same volume under the same conditions, they would have the same number of particles. That's true. Physicists later sat down and ran all of this information in a computer and did some calculus and physics stuff that you don't really even need to know. And they figured out that this magic number is called a mole, and it's 6.02 times 10 to the 23rd. Avogadro didn't just like have a dream and come up with this magic number. He just came up with this idea. So for number 17, the answer is 1. And the reason is because a particle is either an atom or a molecule. It is an interchangeable word for atom or molecule. Because these are both monatomic gases, the answer is atoms. If we had helium, which is monatomic, versus hydrogen, which is diatomic, then we would have to use the word particles, because this guy would be a molecule and this one would be an atom. This is a molecule because it has two atoms bonded together. So 17, is number 1. Okay, question 18. Which statement describes a chemical change? We have alcohol evaporating. That is a physical change. Anytime we have a phase change, it's a physical change. They both start with P. Actually, they both start with pH, if that helps. Water vapor forms snowflakes. Snowflakes are just ice crystals. That's another physical change. Table salt, NaCl, is crushed into powder. Let's try this. Here I have a sheet of paper. It's still a sheet of paper. Nothing changed about it. If I took it and lit it on fire, that would be a different story. Then choice 4, I have glucose and oxygen are used to produce CO2 and H2O. That is a combustion reaction, actually. Reaction. It's a chemical reaction. If it's a chemical reaction, then it's a chemical change. So 18 is 4. Number 19, which statement describes the particles of an ideal gas according to the kinetic molecular theory? Okay. I'm going to write the kinetic molecular theory and then I'll flip it around so you can see it. But the kinetic molecular theory is used to describe how ideal gases operate. When we have gases under these listed conditions, it'll be an ideal gas. So we have no intermolecular forces. We have that they move in random, constant straight lines. This is like the bouncy balls being dropped down the stairs. They have negligible, how do I spell this? Negligible volume, which in other words mean they have ignorable volume. They have no intermolecular forces, and they are separated by very large distances. So that is like in a solid, we have things like really packed up close together. In a gas, they're like all over the place, separated really far apart. So that's that. That's your kinetic molecular theory. When your gases are under when your gases are acting like this, we call them ideal. And the reason for that is that if they are ideal gases, we can use algebra to solve any math problems we have with them. If they're not ideal, then we have to use calculus. And like I've said from the beginning of the year, chemists are lazy. They don't want to do calculus. If they can have an ideal gas and do algebra, they are much, much, much happier. So kinetic molecular theory just describes how an ideal gas works. And for number 19, the thing that fits is here on the list is number 2, and in our answer is also number 2. So 19 is 2. Number 20, which sample of matter is classified as a substance? Now, for your classification of matter, you have matter. Let me do this. You have matter, which is characterized into substances. I'll flip it around in a sec. You have substances and mixtures. Your substances are either elements or they are compounds. Elements can be either monatomic, for example, that's helium, neon, gold, mercury, things like that, or they can be diatomic. This is Brinkelhoff, Brinchlhof. Those are your diatomics. Compounds, that's good. Your mixtures can be either homogeneous, homogeneous, if you prefer. This means same throughout. Or they can be heterogeneous, which means they look different throughout, which I have described as layers. Okay. Which sample of matter is classified as a substance? So you would have to look at the answer choices. Air is technically a mixture. It is a homogeneous mixture because air looks the same no matter where you look. And it's a mixture of nitrogen, oxygen, argon, CO2, water vapor. These are things that you already know. Ammonia is NH3, which would make it a compound, which would make it a substance. This is choice 2. Milk is a mixture. It's a homogeneous mixture. Milk is, if you've ever seen it on the label, sometimes it's called homogenized milk, which really just means, actually, milk is a mixture. If you took milk out of a cow, the fat will rise to the top, and then the milk will be on the bottom. And what happens is that the ratio of fat to milk is going to be like heavy cream, half and half, whole milk, 2%. All of those different types of milk come from the mixture of fat and milk that they put in it. And when it's homogenized, that means that these two are mixed very, very well so that it doesn't form layers inside your milk container. And then seawater, you should know, is a homogeneous mixture of salt and water. So the only substance listed is the compound ammonia, NH3. So 20 is choice 2. 21, which element has the lowest electronegativity? There's 2 ways for you to know this. The first one is the more obvious one, which is on table S. You can look up the electronegativity for each of these elements and fill them in, and whichever one's the lowest is your answer. That's probably the safest way to do it so that you can't get it wrong. The only way you would get it wrong is if you read the table incorrectly. It's almost like it's a free question, honestly. If you went the other route and used your periodic trends to answer this question, that would mean that you looked at the periodic table and you remembered that electronegativity is highest right here at fluorine. Its electronegativity is 4.0, and that's because it's dying to get electrons. Francium, all the way on the opposite end of the table, has the lowest electronegativity. The reason for this, if we go back to this question here, fluorine also has 2 shells, but out here it has 7 electrons. And francium has 7 shells, which is actually 1 more than what's listed here, and has 1 valence electron. So it kind of goes back to that shielding thing where the last electron out here on the 7th shell is not very closely attached or attracted to the nucleus, so it can fall off very, very easily. The electrons here are super close. Fluorine is dying to get 1 more, because if it gets 1 more, then it'll look like neon. And these noble gases are the cool guys on the table, and everybody wants to look like a noble gas. Like everybody does. Even the noble gases want to stay noble. They don't want to look like anybody else. These guys have a full valence shell. So they are happy and don't want to do anything. And everybody wants to be like them. Fluorine, dying to look like neon. Francium over here is like, well, I have all of these electrons and they're 1,000,000 miles away from my nucleus, and I don't really care how many electrons I have. I would just rather let that last electron pop off and disappear, and then I'll look like radon. I don't have to gain any. And that's what electronegativity is. It's the attraction for electrons. So who wants an electron the baddest out of all of these? Fluorine really wants an electron. Chlorine wants an electron pretty badly, not gonna lie. Chromium is all the way over here. Its electronegativity is probably somewhere on the lower side because it's a metal, and metals like to lose electrons, not gain them. And same with francium. Francium's a metal, and it would rather lose an electron to look like radon than it would to gain all of these electrons to look like UUO. So that's the second way you can answer it. So that makes 21, 1. Okay. 22. At standard pressure, methane, CH4, boils at 112 Kelvin, and H2O boils at 373 Kelvin. What accounts for the higher boiling point of H2O at standard pressure? Okay. You could eliminate metallic bonding because H2O is not a metal. It doesn't metallically bond. Those are these guys, like these guys here that are metals, except for hydrogen. Hydrogen is not a metal. That's why it's separated from here. So all of these guys in here are metals. They're going to metallically bond. Ionic bonding. H2O doesn't ionic bond. It's not a metal and a nonmetal. It's 2 nonmetals, so that one's out. Then we have covalent bonding, which we can eliminate because both of them covalently bond. How does covalent bonding help hydrogen, help water have a higher boiling point, but not methane? They both covalently bond, but it's not the answer, which leaves us with hydrogen bonding. Hydrogen bonding is the attraction for, it's an intermolecular force. So when you have water molecules, you have HOH, and it kind of looks, oxygen has these lone pairs on it. It has a higher electronegativity, so this is going to be your partially negative. This is going to be your partially positive. It's an unfinished 8. Is that partial symbol? This negative end of the molecule is going to be attracted to the positive end of another molecule. These guys are like kind of attracted to each other, and that's why water will like stick to the inside of a water bottle. It will stick to the walls of a shower. It will stick to a car. It sticks to grass. It sticks everywhere, and that's because this negative end is attracted to this positive end. In methane, we have carbon bonded to 4 hydrogens. And if you remember, bend and snap, this guy is completely symmetrical. If it's symmetrical, it's nonpolar. This guy is asymmetrical, so it's polar. And it's asymmetrical because it has to be symmetrical in the plus sign, and it's not where this guy is. So this is symmetrical, nonpolar, asymmetrical, polar. Because it's asymmetrical, it has these very strong intermolecular forces. On top of that, because hydrogen is super small, it has what they very incorrectly named hydrogen bonding. Hydrogen bonding is a horrible name for it because it has nothing to do with bonds. These guys are forces. This is a force. It should be called a hydrogen force, but chemists are dumb and named it wrong. So we have hydrogen, and anytime hydrogen is on a molecule with fluorine or oxygen or nitrogen, it's going to hydrogen bond force, where the hydrogen is extra sticky to the fluorine, oxygen, or nitrogen. Chemistry is so fun, right? That's how you remember this? Chemistry is so fun. Hydrogen bonding is incorrectly named, and that makes it fun. I'm sorry, that's really cheesy, but that's how I always remembered it. So hopefully it'll help you too. But that is that. Hydrogen has hydrogen bonding, where this is going to have the nonpolar IMF, intermolecular force, and that has a few names. It is called the van der Waals force, van der Waals with 2 L's forces. It is also sometimes called London dispersion force. It is also called the temporary dipole force. It has 3 names. 1, 2, 3. Van der Waals, London dispersion, or temporary dipole. Those are all proper names. By the time we get to question 30, we're going to take like a 5-minute break because I need to get a glass of water. But I want to get through the end of this section first. Okay. For question 23, we have a mixture of sand and table salt, and it can be separated by filtration because the substance in the mixtures differ in what? Okay. Filtration is one of the ways we can separate mixtures. There's actually a few ways we can separate mixtures, and how we separate them is based on their 2 differences. We have chromatography, which is based on polarity, molecule polarity, whether it's polar or nonpolar. What happens is that we have like this column, and you may have done this in living environment, where you have like a sheet of filter paper or like coffee filter paper, and you usually put like a dot of ink down here, and you put it in this solution, and then it climbs up the paper. and then you'll have like a rainbow come out, which is why they call it chromatography. So if it's like a sheet of black, if it's a sheet of white paper and a dot of black ink, it may be like a green based black where you have like the green coming all the way up here. They do the same thing with like tanning oils. Like sometimes you get a tanning oil that's kind of like greenish or kind of orange-ish. So like the colors will climb up this paper depending on whether they're polar or non-polar and whether the paper is polar or non-polar. Sorry if you can't see the colors. The long one's green and the short one's blue. That's one way that we can separate mixtures. Then we have, and this is going to be like in some type of dish with a liquid in it to get that ink to break apart. Then we have distillation, where you're going to have a boiling flask, which is like almost like a Christmas ornament kind of shape. This is going to have 2 liquids in it. And it's going to have a flame underneath. You're going to be heating it up. Let me see. Here's orange. Here's a flame. And you have like a tube in here that's going to catch it. The vapors, as they evaporate, it bends. It goes up into this tube. And in this tube, we have one tube like this. And then it goes down like that. And then we have a tube that goes around this tube. So, and then we have like a dripper here, and then we're going to catch all of this in an Erlenmeyer flask. So, there's usually like a thermometer in here as well. Whichever one has the lower boiling point is going to evaporate, come up through here as a gas, come up through here as a gas, and it goes through this inner tube. The outer tube is filled with cold water, and this, sorry, I have a new pen. There's a wax tip on it. Oh, this is going to be fun. This has a wax, sorry, no, this has cold water circulating around this, so it kind of cools this gas back into a liquid to the point where it'll drip out of here. And then you can catch it in the Erlenmeyer flask, and you'll have one liquid. Whichever one has the lower boiling point is going to come through. It condenses in what is called the condensing tube, and it comes out as a liquid. And then your whichever one had the higher boiling point is still going to be over here. If you continue to heat it, then it'll come over and it'll remix unless you pull out the first liquid first. And usually, if you're trying to be like super exact, you'll do one distillation, and then you would take this, you would actually take what was left over, cool it down, and distill it again to make sure that all of this first liquid comes out. The next way is filtration. And this is distillation, you're going to separate by boiling point. Sorry, I didn't write that. Filtration is separation based on particle size. And this, you're going to have like a funnel almost, and it's going to have like a coffee filter inside of it. They actually call it filter paper, but there's like a coffee filter inside of it, and you would pour a mixture in here. So let's just say it's sand and water, because that's an easy one. So your sand and water gets poured inside. You're a smart human being. You can figure out that the sand is going to get stuck to this paper and the water is going to come out. The reason for that is that the water molecules are smaller than the particles of sand. The sand gets stuck behind. Then what usually happens is that a chemist would take this filter paper out, lay it flat, and have the sand dry. Sometimes they'll take it out and they'll put it in like a chemical oven and have the water evaporate out of it. It depends on what the mixture is. If it's something that is like flammable, they wouldn't put it in an oven because that would be dangerous. But it depends on what the mixture is. This is a separation by particle size. It's the same thing that happens in your coffee machine. You pour the hot water over and the water is going to dissolve a little bit of the coffee. When the coffee is small enough, it can pass through, and then you'll have a hot coffee on the bottom, and the big fat grounds stay on the top. So when you separate by filtration, you're separating based on... Oh, this is good. I didn't answer the question. Mixture of sand and table salt can be separated by filtration because the substance in the mixture. Okay. They do have different boiling points, but that's not why filtration works. They do have different densities, but that's not why filtration works. They do have different freezing points, but that's not why filtration works. This to me is not a great question. And the reason for that is because the answer is solubility in water, but it doesn't mention anything about water. This is something that you would need to know, that table salt would dissolve in water. So if you put it in a filter like this, let's say you put these two in a filter, you had a funnel, and it was lined with the paper, and inside went your mixture. None of it would be able to come out because they would both get stuck in the filter paper. But if you had added water on top of that, the salt would dissolve, and on the outside you would get NaCl aqueous, and the sand would stay up here. Uh-oh. I don't know if you heard that. The dog baby's getting in trouble. He's beating up my other dog. Okay, so that is number 23. I think that's really the hardest question we've encountered so far. Man, I need a snack. I'm getting hungry. Number 24, systems in nature tend to undergo changes of what? Think of yourself. You. This is nature prefers Netflix and bunny slippers, right? Nature does not like to be active. Nature does not prefer high energy. You are nature. You are part of nature. You would prefer to sit around and do nothing. Then, hi, Coop.
Sorry, I didn't know. Dad told me you were teaching.
I am.
Come here, Coopy. Sorry.
That's okay.
Coop, come.
Oh, goodness gracious. Okay.
Sorry.
You are part of nature. You don't like to be active. That was really cute. He came down with a toy. He wants to play. You don't prefer to be active. You don't prefer high energy. So choices 3 and 4 can immediately be thrown out. Then we're looking at entropy. Entropy is the level of disorder. Entropy is a measure of disorder or chaos or messiness. And I'm the perfect example of entropy. If you've ever been inside the chemistry classroom, it's disgusting. It's not disgusting, but I have my papers all over the room. I'm a giant mess. So that is the perfect example. Low energy, high entropy. Think of Miss Nicholas, lazy and messy. That's the way nature likes to be. Question 25. In the wave mechanical model of the atom, which is this fuzzy cloud of probability, this crazy model, in the wave mechanical model of the atom, an orbital is the most probable location of what? This is usually a question 1 or 2. Usually, probably like a 3 or a 4. like on the test, it's usually the third or fourth question. Here somehow it wound up being number 25. But anyways, in your orbitals, or these fluffy clouds of probability, you're going to have the most probable location for an electron. We've gone over that. That was an easy one. Okay. Functional groups are used to classify what? Functional groups should send you to table R. Table R. Here is table R. And coincidentally, this being number 26 on the test, functional groups are part of organic molecules. It was that easy. This is the easiest question, I think, so far. Functional groups are used to classify organic compounds. That was done. That's it. Okay. That's only page 1 and 2. Oh boy. We have a lot to go. That's okay. It's a yucky day. What else could you possibly be doing today? I mean, come on. It's Saturday. Wouldn't you prefer to be doing this than anything else in the world? Number 27. Which compounds contain at least one element from group 17 on the periodic table? You are looking at aldehyde, amine, ester, and halides. Well, if you remember, group 17 are called halogens. Halogens are halides. Halide just means it's bonded. Ide. So that's number 4 based on that. If you forgot that, table R, if you look at all of these functional groups, you look at the aldehyde. Aldehydes have an oxygen. Oxygen's part of group 16, not 17. Oxygen is 16, not 17. Then we are looking at amines. Amines are down here. Amines contain nitrogens, and nitrogen is part of group 15, so that is not the answer. Then, I'm sorry, there's dog hair all over the place now. Then choice 3 is ester. And ester contains, again, oxygen, which is part of group 16. And then lastly, choice 4 is halides. Halides contain fluorine, chlorine, bromine, or iodine, which are all members of group 17. That was another reference table question. Okay, that one wasn't bad. I told you organic questions are really just reading the tables. Organic questions, as much as I hated organic chemistry in college, organic in Regents is probably one of the easier units. Okay, moving on to 28. In a propanal molecule, an oxygen atom is bonded with a carbon atom. What is the total number of pairs of electrons shared between these atoms? This is going to require a drawing. Propanal. If it has an AL ending, that means it must be an aldehyde. It says so right here on table R. Propanal is an aldehyde. Propanal has already been drawn for you, which makes it a really easy thing to do. You could also draw it out yourself if you prefer. I like to see all the lines. This is the like condensed formula. I like to see it totally drawn out, so I'm going to draw it. So this says I have a CH3. I'll spin this around for you in a minute. I have a CH3, then I have a CH2, then I have a C double bonded to an O, and then I have an H. If you wanted to double check this, you could use table P to remind you that prop means 3 carbons, and I have 3 carbons here, so that works out. And an aldehyde having an AL ending will tell you that you have this functional group, this double bonded O on the end of the molecule. Here's somebody on the mind. What unit vocabulary do you see the most? I would say the vocabulary from units 1 through 5 come up the most. For me, units 1, 2, 3, 4, and 5. 1 was measurement and tools. This is like converting units, kilo, hecta, milli, deci. This doesn't come up like explicitly. This is a vocab question, but it does come up embedded in other questions. 2 is matter and energy. So that is going to be element, compound, mixture, homogeneous, heterogeneous. What else? That is also law of conservation, your phase changes. That's about that. Atomic theory is going to be proton, neutron, electron. Also going back to matter, that's mixtures, including aqueous stuff. Atomic theory, proton, neutron, electron, atom, shells, subatomic particles, your models of the atom, Dalton, Bohr, the gold foil experiment, that kind of stuff comes up there. Periodic table is the groups that go down, the periods that go across, the metalloids, the metals, the nonmetals, the diatomics that go like this. It's 7. Let me highlight them in pink. Your diatomics, oh no, this is not pink, this is orange. Your diatomics start at number 7 and make a 7. And there's 7 of them. 1, 2, 3, 4, 5, 6. You have to remember to include hydrogen. It's also Brinkelhoff. Then you have the halogens, you have the noble gases, you have the alkali metals that have 1 name, alkaline earth metals, group 2 has 2 names. You have the transition metals, which are weirdos. These guys are your normal metals. That's periodic table vocabulary. And then bonding is going to be ionic, covalent, metallic. Atomic theory, ions and isotopes, average atomic mass. More from bonding is going to be sharing, transferring, polar, nonpolar, intermolecular forces. What else? I'll take all of the vocab words for the whole year and I'll put them on blend space. How about that? Is that a good idea? This way you can see all the words and I'll separate them by unit. But I would say these are the most important ones that you would need to know in order to take the test. The other ones, of course, are important, but if you are cramming and this is all you have time for, these would be the words I would say to study. Sorry, that was kind of a thing, a tangent. Going back to question 28. In propanol molecule, an oxygen and atom is bonded with a carbon atom. What is the total number of pairs of electrons shared between these atoms? Shared between the carbon and the oxygen, you have a double bond. There are 2 electrons in each bond, which means in total you have 4 electrons, which means you have 2 pairs. That's not a 2. I'm writing upside down. You have 2 pairs. So, question 28, the answer is 2. Yeah, I will certainly put up the vocabulary. That's not an issue at all. You just got to give me some time because it's saved in like a million different places. But I will get that for you. That'll be the first thing I do after this live stream is over. Okay, number 29. When a voltaic cell operates, ions move through the what? Okay. this is a tougher question. This requires you to remember what a voltaic cell is and what it looks like. The voltaic cell is the scary looking one, is the best way I can describe it. You have two cells. They are totally separate. You have electrodes, which are just chunks of metal. One is the anode and one is the cathode. They're connected by a wire. Let's say this is your anode and this is your cathode. Your electrons always flow from anode to cathode. Do not worry about saying they flow from the zinc to the copper. They flow from the left to the right. It does not matter. Sometimes they, like if I went like this and flipped it around on you, now left and right is changed. If I took it and I flipped it like this way and then this way, and you were looking at it backwards, then the direction changes again. So don't worry about left and right. Don't worry about metal to other metal, whatever. If you say anode to cathode, you will always be right. That's always the way electrons flow. But this question is asking you about ions. So also in this voltaic cell, these guys are floating in a solution. In a voltaic cell, your electrons leave here. If your electrons are leaving, this becomes positive. Your electrons leave, they come over here. Now this is negative. Now here's where voltaic cells get weird. If all of your electrons are moving from anode to cathode and your cathode becomes negative, your negative electrons are repelled. They don't want to come here anymore. They're actually repulsed. They go back to the anode, and then this positive is not positive anymore. Now it's neutral again. So your battery works for like 1 second and then it dies and then it goes backwards. So what happens is that we have this thing called the salt bridge. It's also sometimes called a U-tube. And we put like cotton plugs on the bottom. And in here, we usually have something like NaNO3, which is always soluble. That's why it's there. When this becomes positive, this negative ion, NO3, is going to flow out this way, come here, and it's going to fix this positive. And now it's going to make this negative. So now your electrons want to leave here. Then you have Na, which is a positive ion. It's going to flow out this way and fix this. And now it's positive, which is also going to pull. So your electrons are repelled from here, and they're going to be drawn over here. Now, if you remember, cations and anions, cations are positive ions. It has a positive in the name. This makes that negative. Cathode is named after cation because it is the positive one. This has a positive in its name. That's where the electrons want to go because it's positive, which means your anode is going to be negative. This is how your ions move around. Your ions move around in a voltaic cell through what is called the salt bridge. Okay. Number 30. When dissolved in water, an Arrhenius base yields which? Now, Arrhenius acids and bases. An Arrhenius acid are things on table K that have an H out front. These guys, HCl, HNO2, HNO3, H2SO4, or that's H2SO3, H2SO4, H3PO4. All these things have H plus as their ion. When these guys dissolve and they're aqueous, this H gets stuck on water, which becomes H3O plus. This H gets added to a water and becomes H3O plus. The name of this ion is on table E because it's polyatomic. It's called hydronium. Those are acids. Bases, which is what the question is asking you, this guy is not ammonia. This is not an Arrhenius base. It's a Bronsted-Lowry base. These guys, though, are Arrhenius bases. These guys have the OH minus ion, NaOH, KOH, CaOH2. Remember to use your tables and your common sense. You definitely can do this test. It's a lot easier than you think it is. The name of this ion is on table E. It's called hydroxide. Right here on table E, you have hydronium, H3O+, and you have hydroxide right here, hydroxide, OH-. There you have it. The Arrhenius base is going to give you the hydroxide ions. That was just putting the tables together. Okay, so very quickly, we are going to take a short break because I need to get a glass of water because my mouth is going to fall off and run away. I will be back at 1:10. Go grab yourself a snack. Go make a PB&J. And then we will start the part B's or 2s, whatever they're called officially. B1. We'll start with question 31. All right. See you in a bit. Okay. Everyone back? I got myself some lunch. Okay. Ow. That's funny. You'd rather watch my live stream than do chores? I'm glad. I'd rather be doing this than chores too. Okay. Moving on to question 31. Here we go. What is the total number of valence electrons in germanium atom in the ground state? This is a vocab question. It's asking you if you know that an atom has an overall 0 charge. Now, it's a combination of vocab and reference tables. If you looked at the reference tables and found out which, table S specifically, and found out which one was germanium, you would have found that it's number 32. 32 is a number of protons because that's its atomic number. In an atom, the number of protons is equal to the number of electrons, which makes this choice 3. It's a combo of tables and vocab. That was an easy question for part B. Okay, now 32. Which element is paired with its excited state electron configuration for an atom of the element? This question kind of stinks. Just because you have to check each one. Now, choice 1, we have calcium. Calcium is number 20, so we should have 20 electrons, which we do, but this is its ground state configuration. I know this because that's the one that's listed right here on the bottom of its box. That's not excited, that's ground. And then we have sodium, which is number 11. It should have 11 electrons. Its ground configuration is 281. This here has 12 electrons. That's not excited, that's an ion. That's not an atom. That would be Na minus 1. That's a negative ion. That's not an atom. Then we have potassium, which is number 19. It should have 19 electrons. So we have 16, 17, 18, 19 electrons there, which is awesome. And its ground state configuration is 2881. If it has 19 electrons and it's anything but 2881, it's excited. This is excited. This answer is 3. It's not fluorine because fluorine should have 9 electrons and this has 10. This is F minus 1. That's not an atom. Okay. Oh, wait, did I answer 31 wrong? Ha! Thank you. Number 31, I answered incorrectly because I didn't read the question. Going back. What is the total number of valence electrons? Miss Nicholas, you are dumb today. Valence electrons. In an atom of germanium in the ground state. Valence electrons for germanium is right here. It's 4. I'm a knucklehead. It's not choice 3. It's choice 4. Because it's asking about the number of valence electrons. Thank you for pointing that out. Okay. 33. Given the balance equation representing 2 chemical reactions, which type of chemical reactions are represented by these equations? This isn't bad. Here we have chlorine and sodium bromide, where it's becoming sodium, chloride, and bromine. If you see here, the chlorine is telling the bromine, get out of here, I want that sodium. Bromine gets kicked out and is now single. This is the home wrecking reaction. This is called a single replacement because the chlorine is replacing the bromine. One thing is being replaced. Then we have sodium chloride breaking down into sodium and chlorine. That is going to be a decomposition, which makes this choice 1, a single replacement and a decomposition. (34) An ion that consists of 7 protons, 6 neutrons, and 10 electrons has a net charge of. Net charge means you are going to add your protons and your electrons together. Neutrons don't have a charge, so we're going to just take that information out of the question. It's there to mess you up. We have 7 protons, which is positive 7, and then we have negative 10 overall. That is a minus 3. So that is choice 2. In chemistry, it doesn't matter if the charge is in the front or in the back. It's interchangeable. That part of chemistry really bothers me. It drives me crazy. I'm eating lunch down here, and the dog, I'm in the basement. The dog is upstairs crying because he thinks I'm going to share with him, but I never share food with him, ever. He's a little nutcase. Okay. 36. Which quantity is equal to 50 kilojoules? All of the answer choices are in joules. So we have to convert kilojoules to plain old regular joules. So we are looking at, I'll flip this around for you in a second. We have 50 kilojoules and we want to convert that to joules. The acronym, King Henry doesn't usually drink chocolate milk. King Henry's dad usually drinks chocolate milk. However you decide to remember this is up to you. We're going from kilojoules to regular joules. If you don't remember, unit is going to be your base units, which are M for meter, L for liter, G for gram, and J for joule. That's all forwards. Okay, I thought I drew it backwards. We're going from kilojoules to regular joules, which means we have to jump 1, 2, 3 to the right. I'm going to take my decimal, which is back here, and I'm going to move it 1, 2, 3 to the right. And I'm going to fill in zeros here. 1, 2, 3. So I have the number 50,000. If I took 50,000 and put it in scientific notation, I would move my decimal back. I wish I had more colored pens here. So that we could kind of distinguish what was moving when, but this green I have is too faint. Okay, let's try pink. Hopefully you can see this. If it doesn't work, just let me know. If I took this and moved it back, I would take my decimal 1, 2, 3, 4 and move it there. So this would be 5.0 times 10 to the 4th. And that's in joules. So that would be answer choice 4. For 37, which compound is formed from its elements by an exothermic reaction at 298 Kelvin and 101.3 kilopascals? Anytime you see endo or exothermic, this should send you to table I. Table I is the one that has all of the equations. You're also talking about formation, which should also send you to table I. because table I is called heat of formation. Where is my table I? All my stuff is getting out of order. Oh, it's not called heat of formation. I'm sorry. It's called heat of reaction. Okay. Table I is at 101.3 kilopascals and 298 Kelvin, which is exactly the conditions we're looking for. And we need to know which is created by an exothermic reaction. The little footnote on the bottom of table I reminds you that if you have a negative sign or a minus sign, you are going to have an exothermic reaction. Can you see that? Yeah, okay. You have an exothermic reaction. So it's asking you which of these compounds is going to be formed with an exothermic reaction. So you're just looking for all of these and finding which one's negative. Here's the weird thing, though. For water, there are two reactions for water. They are right here and here. Oh, I did that wrong. In these reactions, one of them is a liquid and the other one is a gas. And actually what happened on your kinetics test, I had to rescore them because I chose the wrong answer. It was like actually really annoying. This one here is a formation of water gas, and that one is formation of liquid water. So in this case, they're both exothermic, which is fine. Either one would satisfy the answer. But on the specific question that I gave you on the test, it was asking for a number. And I got the number wrong because I chose the gas instead of the liquid or vice versa. The thing with table I to remember is that this forms 2 moles of water. So if we wanted to form 1 mole of water, we would have to take the delta H, or the heat of reaction, and cut it in half because we cut the reaction in half. If we wanted to form 4 moles of water, we would have to double delta H because we doubled the reaction. So what question was that? That was question 37. The formation of water vapor from its elements is exothermic. That makes this one choice 3. Okay, 38. At which temperature is the vapor pressure of ethanol equal to 80 kilopascals? This would either require a calculation or for you to read a table. There's an entire table devoted to vapor pressure. That is table H. Table H. I didn't staple my reference tables together, so now I'm out of order. Table H is vapor pressure. Vapor pressure is how badly these substances want to become a vapor. The higher the vapor pressure, the more easily it's going to become a vapor. So if you see propanone has a high vapor pressure, which means it evaporates very quickly. Ethanoic acid has a low vapor pressure, which means it wants to stay a liquid. It doesn't really want to evaporate and become a gas. This dotted line here at 101.3 kilopascals is standard pressure. That's where we live. So when this dotted line intersects with any of these lines, that is called its normal boiling point, or that's its regular boiling point. If you see water, when it intersects with 101.3, it's at 100 degrees Celsius. That's water's boiling point. Question 38 is asking, at which temperature is the vapor pressure of ethanol equal to 80 kilopascals? These on the side go by tens. So this line here, I'm going to intersect that with ethanol. That is about 73 Celsius, maybe. When you take this test, please write all over it, all over the reference tables. These reference tables belong to you. You are allowed to write all over it. So if you need to write and put in like this is 60, this is 70, this is 80, this one's 90, this one is 100, that's fine. Write all over it. This one goes by tens, this one goes by fives. Whatever you like. So this is going to take us down to about 73. There's even a space here if you needed to like take some notes to remind yourself vapor pressure equals wanna be a gas. That's fine. So this is about 73 Celsius. Okay. 39. At 25 degrees Celsius, a gas in a rigid cylinder with a movable piston, which means kind of like a syringe, like a plunger. It has a volume of 145 milliliters and a pressure of 125 kilopascals. Then the gas is compressed to a volume of 80 milliliters. What is the new pressure of the gas if the temperature is held at 25 Celsius? This is really easy, actually, but it's question 39, and it's the first calculation we have to do. Calculations should send you to table T, which of course mine never printed because I ran out of paper. Hold on. Table T has all of your equations. I didn't run out of paper. Just print. I left all my reference tables out in the car. That's what happened. So this is going to be the combined gas law, which I'll flip for you in a minute. I just want to write it and make sure none of it's backwards. It is PV over T equals PV over T. This is the before and after. Because the temperature is being held constant, it's going to be the same number on both sides. So if you had 40 and divided it by 20 or 80 and divided it doesn't matter. The numbers are the same on both sides. So you can cross them out. This equation becomes PV equals PV, which is Boyle's law. You don't need to know that. You're just going to plug in the numbers and solve for P. So initially we have a volume of 145 milliliters. This is going to be at 125 kPa. We are going to set this equal to the pressure we're solving for and its new volume at 80 milliliters. This is an algebra question. I have my calculator here, so I have 125 times 145. Some people like to write this all out. I'm usually not the type, but you are more than welcome to. There actually is not a lot of workspace in the chemistry test, but you have a separate answer booklet. You have a written answer booklet, you have a bubble sheet, and then you have the test. So you're allowed to write, and you have the reference tables. So you can write all over everything, however you like to do it. You just have to find the space. This is equal to 80p, then you divide by 80. And you get P is equal to 226.56 kPa. Now, that's your answer right here. If you were asked to solve this to the correct number of sig figs, this number here has one significant figure. That's because my decimal is absent. I count from the Atlantic side. Oh no, I'm sorry. This is 80 with a zero, with a decimal. So this has two significant figures. Because my decimal is present, I count from the Pacific side, and my first non-zero number is 8. 8 and all the numbers after it are considered significant. So this is 2 sig figs, which means my answer should have had 2 sig figs, which would have made this 230 kPa. It doesn't actually, this is solved as the correct number of sig figs. So that's how you would know to round it. That's that. If you want a review on sig figs, let me know. I'm entirely out of ink. My table S just split in half. That's actually kind of annoying. Okay. The only thing I don't have is table T. Question 40. A 2,400 gram sample of an aqueous solution contains 0.012 grams of NH3. What is the concentration of NH3 in the solution expressed as parts per million? This is also on table T. It is in the section concentration. There's a formula that says parts per million. Its units are ppm. If you forgot what the units stand for, they are on table D, which is right here. ppm is a measure of concentration, and it is parts per million. So to solve for parts per million, you have part over whole times 1 million. And the part is from the question. It's asking you about ammonia. So the part is 0.012 grams and the whole is 2,400 grams. You take this and multiply it by 1 million. There's your setup. There's your equation. When you solve this, divided by 2,400 times 1, 1, 2, 3, 4, 5, 6 zeros, you get 5. That's not a 5. Some teachers are really good at writing upside down. I am not one of those teachers. So this turns out to be 5 parts per million. There I was circling a unit. Here's the answer. 5.0 parts per million, choice 1. These are the first equations I had to use math. The first questions I had to use math. Everything before this point was reference tables, vocabulary, and a little bit of chemistry. 2 math questions so far. Not bad. Okay, question 41. Which equation represents a change that results in an increase in disorder? There's a few ways to know that entropy or disorder is increasing. One of those things is that you have an increased number of moles. So you will have more moles, which means your coefficients add to a bigger number. You will change from solid to either liquid or to gas, something that's less organized. And also your particles are moving faster, which means you have an increase in temperature. So for these guys, which is an increase in disorder, here you're going from solid to gas. So that one's good. Here you're going from gas to solid. That's no good. That's getting more organized. Solid and a gas to a solid, that's getting more organized. Gas and gas to a liquid is getting closer together and more organized. This is choice 1. That's a vocab question. Do you know what entropy is? Do you know what disorder is? How do you tell me which one is more disorderly? Okay. Sweet. That's pages 4 and 5. We are on to page 6. We are working on January 2012. I am eating lunch. It is quite delicious. I hope everybody else is eating some type of snack too. Okay. 42. Excuse me. Okay. A solution consists of 0.5 moles of CaCl2 dissolved in 100 grams of water at 25 Celsius.
Compared to the boiling point and freezing point of 100 grams of water at standard pressure, the solution at standard pressure has what? Okay, this is the ice cream lab for those of you who don't know. When you take something ionic, or anything rather, you take anything and dissolve it in water, what happens? You have, let's say the blue is water molecules. You have all these water molecules, right? When they try to freeze, they're wanting to stick together and lock in and form a solid. When you dissolve stuff in here, you put stuff in between the water molecules so that they can't lock in as easily. This makes your freezing point go down. If I were trying to boil this, I have water molecules, let's say, and there's stuff dissolved in here. These water molecules are trying to break out and evaporate. If they're trying to evaporate, these pink X's are in the way. It takes extra energy to get them to push past the pink X's to get up. This makes your boiling point go up. I have always described this as an expansion of the liquid phase. So if this is water, it boils at 100 Celsius and it freezes at 0 Celsius. This is when it's liquid. When there's stuff dissolved in it, this is going to expand. It gets bigger and bigger. It stays a liquid for a longer amount of time, essentially. So depending on how much stuff is added in here, your freezing point goes down more dramatically and your boiling point goes up more dramatically. So if you did the ice cream lab, the more salt you added to the ice, the colder it was going to have to get. So the higher the concentration in chemistry, big M, the higher the concentration, the more dramatic this is. The more pieces it breaks into, because it's based on ions, these things are dissolving. So you have, if you had NaCl, CaCl2, and let's say you had glucose or sugar, C6H12O6. Covalent stuff does not break up when it dissolves, so this is going to break into one piece. Sodium, Na+, Cl-, this breaks into two pieces, and then your calcium is a +2, and here you have 2 -1s. Your calcium chloride breaks into 3 pieces. The more pieces you have, the more dramatic this stretch is. So for question 42, the more calcium chloride you dissolve at standard pressure, the solution at standard pressure is going to have a higher boiling point and a lower freezing point. That is choice 3. Higher boiling point, lower freezing point. Okay. 43. Given the balanced ionic equation representing a reaction, what half reaction represents the reduction that occurs? This is redox. Redox is going to be anywhere from like 4 to 8 questions on the test. My guess is that they are the hardest 4 to 8 questions on the test. And that's just because redox requires the most thinking out of any of the other units. Excuse me. There's a lot you have to keep straight. So here you need to know what reduction means. We did this not too long ago, so it should be somewhat fresh in your memory. Reduction, this is GER. Gaining electrons is reduction. 212 really liked saying Leo says girl, because when you gain electrons, they go on the left side of the equation. So we're looking for electrons on the left side of the equation, which is none of these answer choices. That makes no sense. Oh, wait. Yes, there is. I can't read. Here your electrons are on the right. They are products, which means they're being lost. Again, here your electrons are on the right. They are being lost. Okay. We are looking between aluminum and copper. We need to know which one is being reduced. So there's a few ways you can do this. You can start by saying in this equation, aluminum is starting out as 0 and copper is starting out as +2. Aluminum is becoming +3 and copper is becoming 0. So who is gaining the electrons? Actually, you could just match this up. This is saying aluminum is starting out as +3, but according to this equation, it's ending as +3. So it can't be this one. It has to be choice 4. Copper has 2, it's missing 2 electrons. That's why it's positive. When it gains those 2 electrons back, it becomes 0. That's this equation here. You could have also looked at table J. On table J, table J is read in the order JAC. On table J, your anode is on top of the cathode. If you remembered ox, you would remember oxidation happens at the anode, and then red cat, reduction happens at the cathode. So we're looking for which one is going to be the cathode, which one's going to be reduced. If you looked at table J, where's table J? On table J, here is copper, here is aluminum. Copper's on the bottom, which would make it the cathode. This guy is the anode. This is where reduction is going to happen. So copper should be the one to gain the electrons. Choice 4. All right. 44. Given the equation and the potential energy diagram representing a reaction, if each interval on the axis labeled potential energy represents 10 kilojoules, it's kind of hard to see here, but here they are. This is why I'm saying right all over the test. Each interval is 10 kilojoules. What is the heat of reaction? This is heat of, you need to know what heat of reaction is. Heat of reaction is delta H. It is equal to products minus reactants. These are your products. These are your reactants. It also tells you that right here. These are your reactants. These are your products. This guy is 0, 10, 20, 30, 40, 50. Your products are starting at 50. Your reactants are at 20. So your delta H is going to be 50 minus 20. 50 minus 20 is going to give you positive 30. For this question, you needed to know this. The rest of it comes out of the question and knowing how to read a graph. All you had to know is delta H is products minus reactants in order to answer this question. Okay. For number 45, I'm sorry, I'm eating my lunch right now. I'm almost finished. Right. Excuse me, 45. Some solid KNO3 remains at the bottom of a stoppered flask containing a saturated KNO3 solution at 22 Celsius. Which statement explains why the contents of the flask are at equilibrium? This is specifically called solution equilibrium. we have a solution. It contains KNO3 aqueous. I'm writing upside down. I don't know how many times I've had to say that today. I just need to defend my handwriting. KNO3 aqueous, and it is in a stoppered flask. So I'm going to draw a lid on this. This is not a flask. This is a beaker, but that's okay. It doesn't matter. A flask looks like this. With the base like that. That's a flask. This is a beaker, but it doesn't matter. It's still stoppered. Stoppered just means closed. You put a cork in it. Now it's stoppered. It's saying that it's a saturated solution, which means there's like some stuff sitting on the bottom, right? Now, this is at equilibrium because I have KNO3 dissolved in here. These particles are going to dissolve at the same rate that a dissolved particle is going to precipitate. Precipitate is the chemistry word for undissolve. Precipitate. So this is happening at equal rates. Because it's equal, the concentration inside the solution and the concentration on the bottom is going to remain the same the whole time. It's constant. So what makes this at equilibrium? The rate of the dissolving is equal to the rate of crystallization. That's the answer. Crystallization and precipitation are the same thing. Crystal is just a fancy name for solid. Having the concentrations remain the same or stay constant would have also been a suitable answer had that been listed. Moving on to 46. 46. Which formula represents the products of the addition reaction between ethene and chlorine, Cl2? This is a tough one. Ethene should be easy for you to draw. Eth, I have 2 carbons. Ene, they're double bonded. Fill in the hydrogens. Here's ethene. You could have also drawn it like this. It doesn't matter how you draw it as long as each carbon has just 2 hydrogens and no more than 2 hydrogens, because each carbon has to have 4 bonds. That's how you count it out. This is like the official way to draw ethene. It doesn't matter. So we're drawing ethene and we're adding in chlorine, Cl2. What's going to happen is that this entire molecule is going to come over and stick itself right here. And it's going to erase this double bond. Now it's only a single bond. So you are adding 2 chlorine atoms. And your double bond is becoming a single bond. That is choice 2. If you have any questions, you can send them on Remind, or you can put them in the comments of this stream. It's just that the comments on the stream are a little bit slower than Remind. Whatever works for you. Moving on to 47. Based on reference table J, which 2 reactants react spontaneously? Okay. For this to react spontaneously, This means that your metals, you're looking at the metals on table J. And whichever one is the element needs to be on the top. So this is where I'm going to write all over table J. We are looking between, in choice 1, magnesium and zinc. Here's zinc, and here is magnesium. There's 2. Then in choice 2, we're looking at copper and iron, Fe. Then we're looking at 3, lead, Pb. Where is lead? Lead. And zinc. Cobalt and sodium. Here's sodium, and here is cobalt. So I want the metal to be active enough to go in and basically break up the compound. So in that case, it is going to be magnesium and zinc because the metal is the one that's on top. The element is the one that's on top, and the compound is the one on the bottom. This guy is really, really stable because he's locked into a compound. That makes him stable. The magnesium has to be aggressive and get in here and break it up, essentially is how I'm going to describe it. If you look at choice 2, copper's on the bottom and iron's on the top. Copper is not aggressive enough to get in here and break up the 2 of these and bond itself to the sulfate. That's just not going to happen. Same with the lead and the zinc. Lead is not aggressive enough to break up the zinc chloride, and cobalt is not aggressive enough to get in and break up the sodium. That's how this works. Table J is like the most annoying table because there's no numbers on it. There's no way to like actively compare, so you have to take everything and compare it just visually like this. You can come into this test with multiple different colored pens. That's fine. It's just whatever you write in the book has to be in a regular blue or black ink. But you can come in with pink pens and orange pens if you want to dress this all up, if you want to start like going crazy on your periodic table and labeling things, that's fine too. It's just anything you write has to be in like the regular blue colored ink, not like the light blue stuff. Okay, for number 48, when the pH value of a solution is changed from 2 to 1, the concentration of the hydronium ions does what? We've already done this, but if you look at table 3, hydronium is H3O+. That's the acid ion. Now, we're looking on the pH scale. pH scale runs from 1 to 14. 7 is in the middle, it's neutral. These guys are acid. These guys are base. We're going from a pH jump from 1 to 2. If you remember, this is a log scale, which means that the difference between here and here is a multiply or a divide by 10. If this were a regular number line, like from kindergarten, you just add or subtract 1. To go from 7 to 6, you would, that's not a 6. To go from 6 to 7, you'd add 1. To go from 6 to 8, you'd add 2. On a log scale, which you'll learn more about in math, I honestly only know enough about logs to do pH, not much more than that. On a log scale, the jump between these guys is going to be multiply or divide by 10. And from 6 to 8, it is multiply or divide by 100 because you jumped 2 places. So if your hydronium ion, if the pH is going from 2 to 1, all those red pens are still on my desk. I need another color. Sorry, I did not mean to shake you. If we are going from 2 to 1, that means I'm adding more H3O plus. I'm adding more H3O plus. It's getting more acidic. When I do that, my hydronium ion concentration is increasing by a factor of 10 because I jumped on a log scale. So 48, we are increasing by a factor of 10. Alrighty. Now we are up to number 49. Given the balanced equation representing a nuclear reaction, which phrase identifies and describes this reaction? Okay. Fission reactions are when we have uranium or plutonium or like some big thing is being shot at by neutrons. We shoot neutrons at it and we break it into like medium-sized atoms like barium. We'll break it into potassium. That's a fission. Fusion is when we take small things and fuse them together to make something bigger. This is 100% a fusion reaction. So choices 1 and 2 are out. If this is fusion, we are taking this. Fusion is what happens in the sun. Hydrogen and helium. Hydrogen is converted into helium right now. Eventually, the helium is going to be converted into carbons, and the carbons into all. This is how all of the elements were made. They were made in stars. E equals mc squared is how we do all of these equations. This is Mr. Albert Einstein. He kind of altered the law of conservation, saying that it's not mass is being conserved as more mass. It's that in total, mass and energy can be converted between, but there's an overall conservation between the two. Does that kind of make sense? It's not like entirely, if you have 10 apples, you have to stay 10 apples. It's that your apples can be converted into trees. And then you have to have the total number of apples and trees together has to stay the same. Kind of making sense? So here you have mass that's being converted into energy because this is mass and we have energy coming out. That's how we get sunlight and heat. Mass is converted to energy. Number 50, and then we are done with multiple choice. Given the equation representing a reversible reaction, we know this because there's 2 arrows. According to one acid-base theory, the reaction that donates an H plus ion in the forward reaction is. This is the little sheep. Bad. Bases accept, acids donate. They accept and donate protons. I can write a proton like this. H plus. Because hydrogen has 1 proton and there's no electron. That's what makes it positive. So the H plus, what is donating the H plus? That's the question. So I always look at these as a before and after. I had NH3 becoming NH4. That had to have accepted, which makes it the acid. And who's donating H2O is losing an H and becoming OH minus, which means that this guy is the donor. Water is the donor. I'm sorry. This is accepting. That makes it a base. I'm silly. This is the acid. That's donating. It's becoming an acid. It's not becoming an acid. It is an acid. Bases accept. Acids donate protons. Okay. Whew. That felt good. Okay. We are like 3 hours in and we've only done 50 questions. But that's okay. That is totally okay. Because we're breaking each one of them down and figuring out absolutely everything, and it's very good review. Okay. So out of all of these questions, there really shouldn't have been more than like 10 or 15 that you were like, man, I'm confused by this. I am confused by this. If you're feeling confused, go to Blend Space and go watch some YouTube videos and brush up on some more stuff. All right. Here we go. B2. Your answers are going in the answer booklet. The answer booklet is going to have like lines with the units for you. You don't have to remember the units. That comes in handy for a lot of people. When you have to balance an equation, there's like blanks out front for you to balance. You can leave them blank. Leaving the coefficients blank is totally acceptable. Here we go. The atomic radius and ionic radius for some group 1 and group 17 elements are given in the table below. Estimate the radius of a bromine ion. All of the things in group 1 are metals. All of the things in group 17 are nonmetals. I'm sorry. That was atrocious. So metals, when they go from atoms to ions, this is MELPS. Metals lose their electrons, they become positive and smaller. You can see that here. We're going from 130 to 78, 160 to 98, 200 to 133. Nonmetals are going to do the exact opposite of MELPS. They gain electrons, they become negative, and they become bigger. So here we're going from 60 to 133, 100 to 181, 117 to a guess, 136 to 220. So you should pick any number that is bigger than 117, but smaller than 220. The reason for that is because a bromine ion should not be bigger than an iodide ion. That doesn't make sense. So anywhere between 117 and 220 would be an acceptable answer. That's as simple as it gets. That's just a data question. That's not even a chemistry question. It's reading patterns and going from there. 52. Explain in terms of electron shells, which means talk about electron shells. Why the radius of a K plus ion is greater than the radius of an Na plus ion. Why is potassium bigger than sodium? Talk about the number of shells. Here is sodium. Here's potassium. Sodium has 3 shells. Let me get some more scrap paper. I'm running out. We have sodium. He's got 3 shells, and then he's in period 3. That's how I know. Plus his electron configuration is 2, 8, 1. Then I have potassium that has 1, 2, 3, 4 shells. And I know this because its configuration is 2, 8, 8, 1. So you would say that the potassium ion is bigger than the sodium ion. Well, this is going to be a plus. It's going to lose this shell, and this sodium is going to lose this shell. So it's just as simple to say that sodium has fewer shells than potassium. Or you could say potassium has more shells than sodium. It's that simple. You don't have to talk about when metals lose shells, they become smaller, but sodium is still smaller than potassium because it has one. Just answer the question that you're being asked. Explain why the radius of K plus is greater than the radius of Na plus. Potassium has more shells. K has more shells. That easy. Really, it's that easy. That's just reading the periodic table, really. Question 53. Write both the name and the charge of the particle that is gained by an F atom when the atom becomes an F ion. F, from right here, F is becoming a negative ion. If it's becoming a negative ion, and it's a minus ion, it is going to gain a negative electron. That is all. It's going to gain a negative electron. That's the name, and there's the charge, a negative electron. For number 54, state the relationship between atomic number and first ionization energy as the elements in group 1 are considered in order of increasing atomic number. What? Okay. Group 1 is these guys here, and we want to look at their ionization energy and give it a trend. So I'm going to look up the ionization energy for each of these guys on table S. And honestly, if you're looking for a trend of the whole group and you are short on time, just pick every other one. Do lithium, potassium, and cesium because it's periodic. These guys are going to follow trends very consistently. You can skip sodium and rubidium and answer the question just fine. I wouldn't skip too many though. Like I wouldn't just pick one, or I wouldn't just pick 2 elements to go off of here because you may lose the trend somewhere in there that it may be too close to tell what's actually happening. So I would pick 3 out of the 5. And you would find out when you looked on table S for first ionization energy, the first ionization energy is going to decrease as atomic radius is increasing. And the reason for that is kind of the same thing that we visited in question 3, I think it was, where we were talking about which electrons had the most energy. Where did that paper go? This one right here. Cesium. 2 of the atoms in question, lithium and cesium. Lithium holds on to this electron very, very tightly because it's close to the nucleus. Because it's close to the nucleus, this electron is held on like crazy. It takes a lot of energy to pluck it off. When you get electrons in cesium that are really far from the nucleus, all of these inner electrons block the pull of the nucleus. The nucleus can't possibly reach this last electron. So the ionization energy, the energy needed to pull off this last electron, is very, very small. And you'd find that out from table S, but that's the reasoning. So you would just write something like that to answer the question, that as your ionization energy, as your atomic number is increasing, your ionization energy is decreasing. You don't have to say why. It doesn't ask you why. The problem that most students have with things like this is that they go beyond stating the relationship. They'll get this part right, but then they try to explain why, even though the question didn't ask for it. They'll say, this is because, and then they explain it wrong. And if you explain it wrong, your state the relationship part is now wrong. Incorrect. Just answer the question that you are being asked. Don't go too crazy over it. Okay. 55. We are looking at a cooling curve. It's a gas starting at 206, and the sample is a substance allowed to cool for 16 minutes. This process is represented by the cooling curve below. This is where I would go through and label everything. So for me, it says it's a gas at 206. I'm going to label this part right here gas. When a gas is cooling, it's going to become a liquid. That's this part here. But the flat part is the phase change between a gas and a liquid. If you don't remember, that's condensing or condensation. Then it's going to become a liquid. Then the liquid is going to freeze and become a solid. So I just go through out of force of habit and I label all of these things. It helps my brain see what's happening. So right here, what is the melting point of this substance? For you to know, you need to know the freezing point and melting point are the same thing. Because they exist at equilibrium, freezing and melting is the same temperature. So freezing and melting is the same temperature. This comes probably to about 90 degrees Celsius. At what time do the particles in the sample have the lowest average kinetic energy? This is a vocab question. And can you read tables? Average kinetic energy is the same thing as temperature. At what time do they have the lowest average kinetic energy? That is time equals 16 minutes. That's when it's the coldest. It's vocab. Do you know average kinetic energy is the same thing as temperature? That's what the question's asking you. They give you all of this table to scare you and make you confused. This is a very simple question. Very simple. Number 57. Using the key in your answer booklet, draw two particle diagrams representing two phases of the sample at minute 4. At minute 4, we are at condensation. Your response must include at least 6 particles for each diagram. So in condensation, we're somewhere between a gas and a liquid. We need 2 particle diagrams. Particle diagram for a gas is, the key may be different. It may look something like this, or it might look something like this, or it might look something like this. However it asks you to draw it is how you're going to draw it. I don't have the key in front of me, but it doesn't matter. I'm just going to draw a gas. Let's say this is a monatomic gas. Gases would look like this. All over the place. Not organized. Kind of crazy. And the liquid I'm going to draw is going to go here. And I'm going to draw it sitting across the bottom and maybe stacked up on itself a little bit. But you have to make sure it's touching all of the edges. If you think about a glass of water, the water doesn't just sit on one half of the glass and fill like this up the lid. You know what a liquid looks like. Draw what a liquid would look like if you zoomed in and saw the individual atoms and molecules. If it says draw at least 6, you have to draw 6. If you draw 5, your answer's wrong. Even if this is correct, if you draw 5, your answer's wrong because you didn't follow the directions. That's an easy question to mess up. So you have to be pretty careful with these. Moving on to number 58 down here. We're looking at some organic molecules, and here we go. 2 hydrocarbons that are isomers of each other are represented by the structural formula and molecular formulas below. These are their molecular formulas. The C5H8, that's the molecular. The structural is showing you how it's built. So, explain in terms of bonds why these hydrocarbons are unsaturated. These are unsaturated because they have double and triple bonds. You have to talk about bonds in terms of bonds. Why are they unsaturated? You could say a saturated hydrocarbon has only single bonds, or you could say an unsaturated hydrocarbon has double or triple bonds. Vocab. Do you know what a saturated hydrocarbon is? That's a vocab question. Chemistry is a language. Question 59. Explain in terms of structural formula and molecular formula why these hydrocarbons are isomers of each other. This is another vocab question. Do you know what an isomer is? why they are isomers. Isomers means they have the same structural formula, which you could figure out from the question. And you could figure out that they have different structural formulas. I described isomers as cotton. Cotton is used to make denim jeans, but it's also used to make t-shirts. They serve very different purposes. They have very different properties. They have different softnesses. They have different durability. I mean, jeans are supposed to last much longer than your t-shirts. Jeans stain less often than your t-shirts because they're built differently, even though they're both made of cotton. That's what an isomer is. Question 60. This is an electrolytic cell. We have the diagram below represents an operating electrolytic cell used to plate silver onto nickel keys. As the cell operates, oxidation occurs at the silver electrode and the mass of the silver electrode decreases. Identify the cathode in this cell. Cathode is where reduction happens. So this is literally telling you that the oxidation occurs at the silver electrode, which means that the reduction or the cathode must be the nickel electrode. The question told you that if you know how redox works. Alternatively, you could have used table J. Now, when you look at an electrolytic cell, table J has to go backwards. And the reason for that, table J is usually read JAC. That is when chemistry magic makes the table work. When the electrons want to move just because of where the metals fall on table J. But the electrolytic cell, if you put a key and silver in water at the same time, the silver is not just going to come off of here and stick onto the key. That's not the way it works. In order to get that to happen, you have to force it. And you force it using this battery. If you have to force it, that means table J needs to be read backwards because your cathode is less active. It's just because you have to force it to happen. This is chemistry magic. This is the voltaic cell. That's the electrolytic cell. So you could have figured it out that way, that the nickel is on top of silver. So nickel, which is right, I've drawn all over it now. Nickel is right here. And silver is down here, which means this is your cathode and that is your anode. The anode is where oxidation is going to happen. That's anox. And here, nickel is your red cat. Nickel is the red cat. 61, state the purpose of the power source in this cell. So the reason you need a battery is because this is, in chemistry terms, a non-spontaneous reaction. Do not talk about chemistry magic. That is just a silly thing I say to help you know that this is a non-spontaneous reaction. What you could say, if you're afraid of the word non-spontaneous, is that this reaction will not occur on its own. This reaction needs an increase in its activation energy. The battery provides activation energy, something to that effect. But the reason you need a battery is because this reaction will not happen on its own. The reason you need a battery in your phone is because without a battery, your phone won't work. The battery allows the chemical reaction to happen. It forces the reaction to happen. Number 62, explain in terms of silver atoms and silver ions why the mass of the silver electrode decreases as the cell operates. Silver atoms are in this chunk of metal. The silver atoms are going to dissolve they leave here and they stick onto the silver. So as silver atoms dissolve and become silver ions, they leave the electrode. The mass of the electrode decreases because atoms become ions and dissolve. When they dissolve, they swim across the solution and they stick to the key. If this concept is confusing to you, which I promise you on some level it definitely is, go to blend space, go to electroplating. There's a lesson in there. It's 11 point something. It's called electroplating. And there is that guy who has like his picture like up in the corner here, and then he's on paper for the most part, and he's like moving the little papers all around, and up in the corner here he's like talking with his hands a lot, like this. And then half the time his hands are like covering the paper. His video on this is actually very, very good. If this is confusing, go watch that, because that's a very good resource. Okay. Moving on. 63 to 65. We are looking at a titration. In a titration, a few drops of an indicator are added to a flask containing 35 milliliters of nitric acid, HNO3, of unknown concentration. After 30 milliliters of 0.15 molar sodium hydroxide solution is slowly added to the flask, the indicator changes color, showing the acid neutralized. Okay. The way a titration actually works in the lab looks like this. Ooh, I just broke something. Oh boy. Okay. A titration looks like this. You have a flask. It says that inside the flask you have in here you have 35 milliliters of HNO3, and you have this burette. Inside the burette, this is the one from the review packet 1, the very first one that we did, where the burette, the numbers are read backwards. 0 is at the top, and then it's usually like 50 at the bottom. So here you know that 30 milliliters of NaOH have been added. They went down and added in, and then you also have an indicator in here. It doesn't say which indicator it is, but you have an indicator and it changes color. And when it changes color, you know that it is now neutral. This is what a titration looks like. We unfortunately did not get to do one because we don't have burettes in the classroom. So here we go. What volume? Oh no, the volume of NaOH solution is expressed to what number of significant figures? We know that the volume of NaOH that was used is 30 milliliters. And here we go. Sig figs. My decimal is present, so I'm going to count from the Pacific side. If you remember America, I cannot draw America upside down, I promise you that. You have like the Great Lakes and New England and now Florida, Texas. There you go. There's America. This is the Pacific Ocean. This one is the Atlantic Ocean. If your decimal is present, P, you start from the Pacific side. If your decimal is absent, you would count from the A, Atlantic side. In this case, it's present. You start at your first non-zero number, which is 3. The 3 and all the numbers after it are considered significant. So this is 1, 2, 3 sig figs. That's it. 63, the answer is 3. For 64, complete the equation in your answer booklet for the neutralization reaction by writing the formula of each product. Okay, so it is going to give you a chemical equation, and that is going to be HNO3 plus NaOH is going to give you blank plus blank. That's what it's going to say in the answer book. It's telling you that this is being neutralized. I should have wrote that like a human. This is being neutralized. When you do acid-base, this is going to be a double replacement reaction, the one where A pairs with D. So you have H bonding with OH and Na bonding with NO3. If this were A, B, C, and D, that's how it would go. So A pairs with D, you get HOH, which is the formula also for water. And then you get NaNO3. It's important to know that Na is +1, NO3 is -1, polyatomic. This comes from table E. When you crisscross this and you bond them, you just get NaNO3. That's a capital O. NaNO3. So that would be the products that you get. For number 65, we are showing a numerical setup for calculating the concentration of HNO3 in the solution. This titration, the word titration, should send you to table T for the titration equation, which is MAVA equals MBVB, which I simplified for you guys. MV of the acid is equal to MV of the base. It doesn't really matter which one you put in because they're set equal. But here, this is going to be your the HNO3 and the NaOH, and all of these information is going to come from the question. So from this very short reading, you have I'm going to transfer this to a nicer sheet of paper. We have MVA equals MVB, where this is HNO3 and this is NaOH. Your M molarity, or your concentration, and V is volume. We don't know the molarity of M. That's actually what we're solving for. The volume of the acid is 35.0 milliliters. This is equal to a molarity of 0.15 molar, and the volume is 30.0 milliliters. This is all you have to do. You only have to set it up because it says show a numerical setup. That's it. All you have to do is plug it in. You don't have to solve it. If you choose to solve it, that's fine, but you don't have to. I wouldn't spend the time. This is all you would need to do. For number 66, it gives you a little story to read. These are the part C's. I think that the part C is like the part B. For the most part, those last questions that we did, with the exception of the electrolytic cell, that I would say is a very easy section because it requires some knowledge of chemistry, but for the most part, it's reference tables. This is where you're being asked to explain more stuff in the part C. So, part C, 66 through 69 on the information below. We have a fireworks display. Salts are heated to very high temperature. Ions in the salts absorb energy and become excited. Spectacular colors are produced as energy is emitted from the ions in the form of light. This should send you back to the Bohr model, where the electrons jump up and down. The color of the light emitted is a characteristic of the metal ion in each salt. That's telling you that every metal ion is going to give you a different color. For example, the lithium ion in lithium carbonate produces a deep red color. The strontium ion in strontium carbonate, SrCO3, produces a bright red color. Similarly, calcium chloride is used for orange, sodium chloride for yellow, and barium chloride for green. Write the formula for the salt used to produce the green light in the fireworks display. Green light comes from barium chloride. That's a reading comprehension question. Green light comes from barium chloride. What's the formula for barium chloride? We actually had a homework assignment somewhere in like December, maybe, write a paragraph explaining what happens when barium and chlorine bond. We have barium chloride. Barium and chlorine. Barium is a normal metal. He's always +2. Chlorine is a nonmetal, always -1. You crisscross these, the 2, not the sign, just the number. 2 comes down here. The 1 jumps over there. You are going to get BaCl2. That's the formula for barium chloride. Okay, 67. Identify 2 types of chemical bonds found in the salt that produces a deep red color. So, according to the reading, the deep red color comes from lithium carbonate, Li2CO3. CO3 is an ion, and this is a metal. So what happens, this metal and this ion are going to have an ionic bond. They have an ionic bond. So that's one type of bond in lithium carbonate. Inside carbonate, we have a metal, a nonmetal bonded to another nonmetal. This is a covalent bond. That is a covalent bond. It is a nonmetal bonded to another nonmetal where they share electrons. Carbonate is going to be carbon bonded to oxygens. This one's going to have a double bond. This is something that we didn't do in Regents chemistry. It's not required of you. It's called resonance. Essentially, this double bond is going to move around. Don't worry about it. You don't need to know how to draw it. All you need to know is that inside this, because it is a bundle, it has its own type of bonding. And because it has 2 extra electrons, it uses those 2 extra to bond with lithium. That's all. So it has ionic and covalent bonding. Essentially, anytime it asks you to identify 2 types of chemical bonds, the answer is going to be ionic and covalent. They do that a lot with these metals bonded to polyatomics. 68, determine the oxidation state of carbon in the salt used to produce a bright red color. The bright red color comes from strontium carbonate. Strontium carbonate. This isn't too old either. Strontium on the periodic table is right here. Strontium is always a +2. Then we have oxygen, which is always -2. I have 3 of them. So in total, this is a -6. All of your strontiums are +2. In total, because this is a molecule, it has to equal 0. So I'm going to put an X in here. In order to get this to equal 0, my X has to be a +4. Lastly, we are looking at number 69. Explain in terms of subatomic particles and energy states how the colors in a firework display are produced. So this is what happens. We have to talk about subatomic particles and we have to talk about energy states. Talking about energy states should make this subatomic particles part ring a bell in your head that says electrons. What happens? We have a positive nucleus and we have shells of electrons. Let's say this is lithium. I have 3 electrons. What happens is I put a fire in lithium. I'm going to use fireworks. I'm lighting this on fire. This electron down here says, ah, that's hot. It absorbs a lot of energy, realistically. This electron jumps up here. It absorbs some energy. It has some extra energy. So it uses that energy to jump up. And now it's having a party with this other electron in the next shell up. When this party is over, the electron has to go back down. When it goes back down, the energy has to come out, and that energy comes out in the form of light. And in lithium, this is going to produce a deep red color. So let's just say this is red. This is going to have deep red light come out, and that's where the red from the firework comes from. This light comes out when this electron leaves, spits out this energy, and goes back to where it came from. So the energy comes in as fire, moves the electron up. The electron has some fun up here, and this is, okay, I'm out of energy, spits the energy out, and goes back to where it belongs. That's what happens. So you'd have to say electrons absorb energy, jump up to the excited state. When they emit is the chemistry word for spit. They emit energy in the form of light when they return to ground state. That's all. And then that's when you hit electrons and you hit energy states. You don't have to specifically say energy states. Excited state and ground state will satisfy this requirement. Number 70. A scientist makes a solution to contain 44 grams of hydrogen chloride gas in 200 grams of water. This process is represented by the equation below. Using table G in terms of saturation, identify the type of solution made by the scientist. We are going to table G for the first time for this whole test. Where is table G? Oh my goodness, there's so much paper here today. That's part of the test. Here we go, table G. Table G is a nightmare. We are looking at HCl, and we are looking at 20 degrees Celsius, and we are looking in 200 grams of water. So that means we have to take our entire table and multiply it by 2. And we have 44 grams of HCl, which puts us about here. For HCl, right here, 44 grams is about there. In 200 grams, we have to take this number and double it, which would put us at 88. 88 is about here. This point for 20 degrees Celsius would actually put us here. The line for HCl is this one right here. If I have 88 grams hold on. No, I'm backwards. You are not adding in this 200. You're not doubling this. You are having it. And the reason for that is because it's telling you flat out, you are putting in 200 grams. That's the answer. It's in 200 grams of water. You are not doubling this. You are halving it because it is looking like it actually is 44, but because you're doubling the amount of water, it's going to act like it's 22. So it's actually going to be down here instead of up here. Any which way, it's going to be an unsaturated solution because the point falls below the line. In terms of the distribution of particles, why the solution is a homogeneous or a homogeneous mixture, that is because we're talking about in terms of particle distribution. If it's homogeneous or homogeneous, your particles are spread equally through the whole thing. If it were heterogeneous, it would look like this, and it would have layers. It does not have layers. We are saying here, equal distribution of particles, like this. That'll answer your question there. No layers. Even distribution, equal distribution, something to that effect. Almost done. If I can find the rest of the text, here it is. Okay. 72, identify one substance in the passage. I didn't read the passage. That would be a good idea, right? Okay. Iron has been used for thousands of years. In the air, iron corrodes. That's kind of like rusting. One reaction for the corrosion of iron is represented by the equation below. In the presence of water, iron corrodes more quickly. This corrosion is represented by the equation below in equation 2. That's not a word. Identify one substance in the passage that cannot be broken down by a chemical change. That is 100% a vocab question. If it can't be broken down by a chemical change, that means it is an element. So, good answers here. Iron, oxygen. Iron and oxygen are the only substances in this reading that cannot be broken down by a chemical change. So this question has 2 answers. And it says identify one. If it asks for one, only give one. If you give 2, your answer is now wrong. Even if you said iron and oxygen, it asks for one. Only list one. 73. Using equation 2, describe one chemical property of iron. Chemical properties describe chemical changes or chemical reactions. So using equation 1 to describe one chemical property of iron, you would say it corrodes in the presence of oxygen. It literally tells you that in the reading. It's asking you specifically if you know what a chemical property is. Chemical properties describe chemical changes, and corrosion is a chemical change. It's all about making connections. Study vocabulary. 74. Balance the equation in your answer booklet using the smallest whole number coefficients. I don't know what the equation is in the answer booklet. I'm going to assume that that is equation 2 because equation 1 is already balanced. So let's see. We have in equation 2, iron plus O2, iron plus O2 plus H2O gives us FeOH2. Yeah, it's this one. So here we have iron, we have oxygen, and we have hydrogen. On this side of the equation, on this side, I have 1 iron. I have 3 oxygens, and I have 2 hydrogens. On this side, I have 1 iron. This distributes through. I have 2 oxygens, and then this distributes through again. I have 2 hydrogens. I need to balance this so that I have the same number of oxygens on both sides. So between 3 and 2, I could change them both to a 6 by multiplication. So to change this to a 6, I'm going to put a 3 out here. Oh, no. This is tougher because your oxygen is split in 2 places. Let's say I put I need to put an odd number. No, I need to put an even number out. Nope. Okay. Did I do this right? Yeah. Okay, if there is a 3 here, then I have 7 oxygens, and then what? What am I looking at here? These are brain busters sometimes, I promise. I actually do need an anything times 2 is going to be an even number. And then if you add 1, it's going to be an odd number. But then to get this to be an odd number, you have to put a coefficient out front and then multiply it by the 2. So let's say I put a 2 here. That makes this a 2. And that means I have 4 oxygens and 4 hydrogens. Then I'm going to leave this alone. I'm going to put a 2 here and a balance this with me. Somebody help me out. If I put a 2 here, now I have 4. Yeah, I got it. Okay, let me do this again and I'll walk you through it. Fe plus O2 plus H2O gives us FeOH2. I have iron, oxygen, hydrogen. Here's 1, 3, 2, 1, 2, 2. You should be able to get at least this far, counting up where everything is, how much you have of everything. Now, this is like a math problem here. If I put any number out here, then this is going to come out to an even number, no matter what it is, because anything times 2 is an even number. And then I have to add this one over here. So I'm going to get an odd number. But it's impossible for me to get an odd number out here because I'm multiplying by 2. So I started by changing this oxygen with this one instead of this guy, because this guy wasn't going to help me at all. So I started here. And even though it is 2 and 2, there's an extra 1 right here. There's actually an extra 2 right here. So I did this. I took I'm trying to do this in different colors. The blue and purple I have are too close. If you put a 2 here, can you see that too? If you put a 2 here, this changes to a 2, and this changes to a 4, and this changes to a 4. Then you have to work on this side. If you put a 2 out here, that changes to a 2. I need to change my hydrogen, so I'm going to put a 2 here. That makes this a 4. And then it also changes my oxygen. So I have, what did I do? No, I did this wrong. No, I didn't. I'm thinking this 2 goes with the oxygen. It doesn't. 2 times this imaginary 1 is 2. Plus this 2 over here gives me 4. Now, this is my smallest whole number ratio, and I know this because 2, the imaginary 1 right here, the 2 and the 2 cannot be reduced. You are going to have a blank line out in front of the oxygen on the test. This can stay blank. You can also fill it in with a 1. Any way you like to do it is still technically correct. Whether it's blank or it's a 1, it is a-okay. Fantastic. Moving on to number 75 about vitamin C. Vitamin C, also known as ascorbic acid, is water soluble and cannot be produced by the human body. Each day, a person's diet should include a source of vitamin C, such as orange juice. Ascorbic acid is has a molecular formula of C6H8O6 and a gram formula mass of 176 grams per mole. Excuse me. What is the color of an indicator? What color is the indicator thymol blue after it's been added to an aqueous solution of vitamin C? So it's telling you that this is ascorbic acid. If it's an acid, you need to look at table M to tell me what the color of thymol blue is. Let's find table M. Table M, I'm looking at thymol blue. Thymol blue runs from 8.0 to 9.6, and here it is yellow, and here it is blue. And in the middle, it's going to be green. So, this side is the acid side, this is the base side. This is going towards 14. This is going towards 1, which means that in acid, thymol blue would be yellow. 76, determine the number of moles of vitamin C in an orange that contains 0.71 grams of vitamin C. There's 2 ways to do this. And the way we did it in class was that you took the given and you multiplied it by the conversion factor. And the rule for the conversion factor was that the mole always gets the 1, always. So in this case, this would be 0.071 grams, which is your given, and you are going to multiply that by 1 mole. And the number of grams in 1 mole is 176 because that is its GFM. This is one way you can do it. You know to put grams on the bottom because the question is asking you for moles, and you want grams to cancel with grams. So you need 1 on the top and 1 on the bottom. Doing this, because this is over 1 and there's no variables, you just multiply straight across. You wind up getting 0.071 divided by 176, and I'm going to calculate that right now. 0.071 divided by 176, and you would get 0.0004 moles, or you could say 4.01234 times 10 to the minus 4th moles. That is the same thing. You could also solve this as a ratio. So to do this as a ratio, you would say, when I have 1 mole, that is equal to 176 grams. But how many moles is it when it's 0.071 grams? You could also solve it this way. And here you would cross multiply and solve for x, which some people prefer to do. It's fine. Anyway, you're going to get the same answer. So when you cross multiply this and solve for x, you are also going to get 0.0004 mole. Now, it's important that you write MOL because that is mole. Little m is meter, which is a distance, and capital M is molarity or concentration, which is 2 very, very, very different things. Mole is MOL. Don't abbreviate it any other way because that's the only way to do it. You could also write MOLE if you prefer. I was always one of those people writing out like sine, cosine, tangent. I didn't like cos, tan, whatever. I'm also the same way with mole. 77. In your answer booklet, show a correct numerical setup for calculating percent composition by mass of oxygen in ascorbic acid. So, percent composition also comes from table T. It is part over whole times 100%. Your part is the number of oxygens. So in ascorbic acid, we have C6H8O6. My whole is 176. It told me that in the question. The part is oxygen. Oxygen, according to the periodic table, has a mass of 16. So it's 16, but I have 6 of them. So that's 16 times 6, which I am mostly certain is 96, but I want to check because I don't want to get the answer wrong. So I'm going to take 16 times 6 because I have 6 oxygens. That is 96. I'm going to multiply this by 100, and that'll tell me the percent by mass of oxygen. Believe it or not, you do not have to answer this question because it only asks for the setup. 78, write the empirical formula for ascorbic acid. The empirical formula, this is the molecular formula. The molecular formula is whatever is in your hand. The empirical formula is the skeleton structure, or when you take this and you chop it up or reduce it as far as it can be reduced. So 6, 8, and 6 can all be reduced by 2. So if I took C6H8O6 and I divided the whole thing by 2, I would get C3H4O3. And if you look at this, it can't be reduced any further, and that makes it the empirical formula. Leave a comment if you're still watching, because I'm curious of who's here. Okay. This is it. This is the last page. 79 through 81. Several steps are involved in the industrial production of sulfuric acid. One step involves the oxidation of sulfur dioxide gas to form sulfur trioxide gas. A catalyst is used to increase the rate of production of sulfur trioxide gas. In a rigid cylinder with a movable piston, this reaction is by the I have more. This way to attempt to relieve the pressure.
No, stop that. Coop, stop. Stop. Come on, let's go outside. Are you kidding? Go. Come on. Come on. Let's go. You just peed on the floor. He just. Yeah, whatever. I'm working. Put him outside. Are you kidding me? Oh, there's people still here. I don't know if this is still going. I don't know if any of that's saved. Okay. I was just disconnected at the same time that my dog had an accident on the floor. Where were we? Goodness gracious. Okay. I'm sorry. Okay, where were we? Number 40. Goodness gracious. 40. What am I talking about? Okay, so 79 in terms of collision theory, the number of collisions increases when pressure increases, so the equation shifts this way to relieve the pressure and get back to its normal number of collisions. Determine the amount of heat released by the production of 1 mole of SO3. You want to divide this by 2 to get 1. That's what I want. In order to do that, I have to take delta H and divide that by 2. So that's 392 divided by 2, and that is 196 kilojoules. You don't have to explain how you did it or whatever. You just need the number. State in terms of the concentration of SO3, what occurs when more O2 is added. So if you add more O2, remember the rule for equilibrium is add away
take towards. So if you add oxygen, the equation shifts away from the oxygen. So you would just say SO3 increases, and this is going to be decreased. If you add in a bunch of extra oxygen, the equation is going to work to absorb this SO2 and use these two together to form SO3 to get the number of oxygens back down to where it's supposed to be. Last ones, 82 to 85, and then we can finally call it. Nuclear radiation is harmful to living cells, particularly to fast-growing cells such as cancer cells and blood cells. An external beam of radiation emitted from a radioisotope can be directed on a small area of a person to destroy cancer cells within the body. Cobalt-60 is an artificially produced radioisotope that emits gamma rays and beta particles. One hospital keeps a 100-gram sample of cobalt-60 in an appropriate secure storage container for future cancer treatment. State one risk to human tissue associated with the use of radioisotopes to treat cancer. Radioisotopes can cause cancer. It says in the first sentence, nuclear radiation is harmful to living cells, particularly to fast-growing cells such as cancer cells and blood cells. So you would say radiation is harmful to living cells. That's straight out of the reading. Compare the penetrating power of the two emissions of cobalt-60. Cobalt-60 emits gamma and beta particles. Gamma versus beta particles is that gamma is all energy, so this has a higher penetrating power. So that's it. Gamma radiation has a higher penetrating power than beta particles. 84, complete the nuclear equation in your answer booklet for the beta decay of cobalt-60. So that would be cobalt-60 is emitting beta particles, and it becomes what? So we've done a million of these equations in class. Cobalt is number 27. The mass number is going to stay 60, and the atomic number is going to be 28, because 28 plus a -1 gives me the 27. And lastly, question 85, determine the total time that will have elapsed when 12.5 grams of the original cobalt-60 sample at the hospital remains unchanged. So this is a half-life question. We have, find a blank sheet of paper. Here we go. We are comparing, determine the total time. That's what I want to figure out. So I have half-life, and then I have mass. So according to the reading, we started with 100 grams. And that is at half-life equals 0. Then at half-life 1, I'm going to have 50 grams. At half-life 2, I'm going to have 25 grams. At half-life 3 is when I will have 12.5 grams. This is what I want to know, but I need to know how much time this is. I know from table N that one half-life for cobalt-60 is 5.271 years. So I'm going to take that 71 years. And I'm going to multiply that by 3 half-lives, and this is going to be approximately 15.7 years. And that is all. I'm sorry for the breakup and the disturbance. That is it. There is a review at school 9 a.m. on Monday. There will be some snacks, but still bring your own. Don't rely on me to feed you, because I have no idea who's going to be there. So first come, first serve. That's all. If you're there at 9, you will have a snack. If you're there at 9:15, I cannot guarantee a snack. That's all. Any questions, ask me on Remind. Check out Blend Space for other review videos, class notes. I will put the vocab up for those of you who asked for it. And the test is Tuesday morning officially starts at 9:15. You need to be at school like at the latest 8:45. I really can't think of anything else. You should bring a pencil and a pen to the test. You will need a pencil for the bubbles, a pen for the answer booklet. You will get a reference table. You will get a calculator. That's it. Just bring a pen and a pencil. That is all. I hope to see you all Monday. If not, I will see you Tuesday for the test. I will be there. So